Gazing at the stars is like looking into the past. All of the twinkles you recall seeing from Earth are very old. By the time its light reaches your eyes, even the nearby Alpha Centauri system has been gone for over 4 years. This is even more potent for behemoth stars. They can illuminate entire galaxies, even momentarily surpassing the combined brightness of all the other stars in the galaxy. These are luminous giants, enormous bodies, whose brightness is a result of violent fusion and tremendous energy, rather than just being for show. Even the brightest of them pale in comparison to the scale of interstellar space. Although light travels quickly, the universe expands even more rapidly. One great enlarged supergiant star's light has been traveling for 10,000 years and is now passing by your invisible shoulder as you float past it. There is more to a star's brightness than just its power. Perspective is key, as is the difference between apparent brightness and luminosity. A candle close by can shine brighter than a bonfire far away. However, astronomers have discovered a way to use the inverse square law of light to unravel this illusion. The light appears 4 times dimmer with every doubling of distance. Therefore, you can tell that a star like R136A1 must be genuinely luminous to appear as bright from Earth when you see it burning at its core with temperatures above 50,000 Kelvin. One more star is Deneb. The brightness of a blue-white supergiant in Cygnus is comparable to that of other nearby stars. Its light left around the time that ancient Mesopotamians were constructing ziggurats, even though it is almost 2,600 light-years away. And only now did it come steadily and silently to us. A reminder that there is more than space. It is replete with photon-based narratives. You picture yourself moving as fast as light. Even then, you realize that it would take 100,000 years to travel across the Milky Way to get to this quiet arm of the galaxy. But light makes the trip every second without getting tired. Time and momentum are all that are present. There is no engine or vessel. You begin to perceive a subtle truth as you float. The language of the universe is that starlight. Each wavelength conveys a message, such as a chemical signature, temperature, or speed. And the universe documents its narrative, in spectra, like a silent archivist. There is one such tale to tell. Even before you get there, you see it. A dim red glow on the brink of night. Interstellar dust filters out the distinctive glow of hydrogen alpha emissions. It denotes another giant's territory. You slow down out of respect rather than fear. The star in front of us, Stephenson 218, is located at the boundary of known stellar dimensions. Its radius is more than 2,100 times that of the Sun, according to some models. Its edge would extend past Saturn's orbit if it were situated in our solar system. But before you reach your thoughts, it is cloaked, hidden, a ghost in the haze, so you could fly past it and never really see it. It lingers on this moment's scale. Even after traveling dozens or even hundreds of light years, you have only encountered a small number of members of this uncommon giant family. Like red dwarfs, the majority of stars in the universe are tiny, faint, and long-lived. They burn silently for trillions of years. The loudest and shortest-lived stars that form galaxies are all around you, though. Stars that will soon disappear, leaving behind only gravity, dust, and heavy elements. This realization has a faint ache. That genius is short-lived. The strongest lights dim the most quickly. However, that is also normal. That is also lovely. According to some astronomers, we still don't fully understand the upper limit of stellar size. Fusion and gravitational balances can be modeled, but the calculations are made more difficult by turbulence, magnetic fields, and stellar winds. Although observations are helpful, stars such as Stephenson 218 are hidden behind interstellar gas veils. It is only discernible in tiny bits of radio and infrared data. Some people doubt its exact size. It might be a cluster, according to some. However, it currently occupies a silent place in our records, a record of scale rather than ego. The light becomes deeper and redder as you approach. Only the longest and warmest reds can travel through dust because short wavelengths are scattered. It feels like you're floating into an endless sunset, and space remains silent to this day. There was only the endless starlight, no flicker of sound, no roar of fusion. You come across the massive red supergiant star UI Scuti, which is located near the edge of a known stellar scale. You slip silently into UI Scuti's domain and arrive without making a sound. There is only a slow expansion of warmth and light, thick as breath, with no solid edge to cross. Now, you are hovering close to one of the brightest stars ever measured by volume. Situated in the constellation Scutum, this red supergiant is roughly 9,500 light-years from Earth. In terms of visible light, the star is not bright. Its energy is weakened by the vast distance and the dust that floats between galaxies. What you see is warm rather than blinding. It emits a long, languid light across the void, glowing in the deep red and infrared regions of the spectrum. It's weird to think of UY Scuti. Although it was a single body, its surface might include the orbits of Earth, Mars, Venus, and Mercury. It is neither solid nor well-defined, and it takes more than 7 hours for light to pass through it. Its edges disappear into the void. The heated gas in its atmosphere is constantly rising, falling, and escaping into space. The temperature and pressure inside this star's massive convective layers are continuously resisting the gradual pull of gravity. The radiation produced deep within the core is powerful enough to push the outer layers outward, causing them to swell. The star becomes brittle and unstable as a result. Large gas cells are scattered across the star's uneven surface. According to some astronomers, the convective cells of one of these bubbles may be larger than the Earth's orbit. Fusion continues to take place at the core of this growing giant. Helium is currently combining to form heavier elements, such as carbon, oxygen, and magnesium, as hydrogen has long since been depleted. This stage is crucial. The end of the star is in sight. Iron, a crucial boundary in stellar physics, forms when the core becomes too heavy to withstand collapse. Energy is not released when iron fuses. It takes it in. The star will implode, and the balance will break when that time comes. However, that is still a ways off. Currently, UY Scuti pulsates slowly, resembling the heartbeat of the cosmos. Because its brightness changes as its outer layers expand and contract, it is categorized as a pulsating variable star. The star gets its rhythm from this slow-breathing cycle, which lasts for months and is comparable to the tide's ebb and flow. From where you are, you notice another oddity. UY Scuti is losing mass. Star winds, which are streams of particles blown by radiation pressure, carry their outer layers away as they drift. This process breaks the star down over time. Astronomers argue over its precise size in part because of this. It's hard to tell where the star ends, because the outer envelope is so diffuse. Take a moment to consider how little of this was understood only a few decades ago. During the 20th century, red supergiants were considered uncommon and enigmatic anomalies. We didn't start mapping their precise dimensions until the advent of space telescopes and the development of accurate spectroscopic techniques. Furthermore, some data are still up for debate. Uncertainty doesn't lessen the wonder despite disagreements over temperature variations, mass loss rates, and distance estimates. It enlarges it. According to some researchers, UY Scuti may shrink over time. Before the final supernova, UY Scuti is progressively collapsing into a smaller, hotter star due to internal changes and mass loss. Others think that its next contraction might be the last, and that it might already be at the precipice. Such a star would not only have a bright supernova, but also an exceptionally bright supernova. It would change things. An entire galaxy could be outshone for weeks by such a massive energy release. Space would be flooded with neutrinos. In that furnace, elements like uranium, platinum, and gold would be created. Cosmic alchemy is what this is. To add complexity to the universe, stars change into intricate structures. But that time hasn't arrived yet tonight. You float next to a star tonight that is so big that the scale makes your head spin. Its texture, its surface's slowness, and its core's peaceful distance. Even in this vastness, you feel as if you are orbiting an entire planet, rather than just one star. It's not just UY Scuti. There are still more giants to come, some even bigger than the others. With your thoughts still following, you start to distance yourself. Like a dream's afterglow, the red light lingers in your eyes. The space ahead is not empty, but it is dark once more. In the far silence, there is another great pulse. This one is more obscure and less well known, but it may be even more significant. People debate it quietly and whisper its name among catalogues. Stevenson is 18 years old. You start to glide slowly deeper into the world of hypergiants as you turn towards it, allowing the light of UY Scuti to fade behind you softly. You discover the reasons behind the disparity in size between stars and how this impacts their destiny. The red glow of UY Scuti fades behind you as you continue, like a sunset disappearing beneath the horizon. The vast, calm expanse of space ahead is a painting of delicate light and gravitational tension. The physics beneath the stillness hums with complexity, but you move through it. Size isn't always what it seems out here. Even though a star may grow to the edge of Saturn's orbit, it may only have a small portion of the mass of a hotter, smaller star. The difference between mass and volume becomes vital in astronomy. You allowed your mind to wander through this silent contradiction. For instance, UY Scuti has a huge radius and a massive mass, but it is comparatively small for a star of its type. It has 7 to 10 times the mass of our Sun. Contrast that with a star you will soon encounter, such as R13601. Despite having a much smaller diameter, that one might hold close to 200 or even 300 solar masses. It burns intensely due to its unfathomable density and fusion rate rather than its sheer size. Why is that? Think about how gravity and pressure are balanced at each star's core. Everything is drawn inward by the gravity of a massive star, but radiation is released when fusion at the core pushes outward. The star's size, shape, temperature, and lifespan are all determined by this balance. The pressure at a star's core increases with its mass. It must fuse elements more quickly to maintain balance. That intense activity shortens its life, but it also makes it brighter. It could take a giant like R13601 a few million years to burn through its fuel. While not all massive stars have a large radius, a smaller star can shine continuously for tens or even hundreds of billions of years. Many are compact and extremely hot, such as Wolf-Rayet stars and blue giants. They are compressed or stripped of their outer layers. Some are hardly 10 times the size of the radius of our Sun, even though they burn brightly. The expansive atmosphere of a red hypergiant is unlike anything else in the universe. It's like equating a mountain-sized smoldering ember with a bonfire. Both glow and burn, but one is diffuse and slow burning, while the other is intensely short-lived. This tension shapes every stage of a star's life. Mass is fate, too. When a star dies, its mass dictates what it becomes. If it starts with less than 8 solar masses, it may grow into a red giant before quietly settling into a white dwarf and gradually cooling over trillions of years. However, it will end in a black hole, a neutron star, a supernova, or another catastrophic event if it begins with more than 20 or 30 solar masses. As you drift, you silently pass through thresholds. The line separating peacefully ending stars from violently collapsing ones is somewhere behind you. The point at which space folds inward, and even neutron stars can no longer sustain their mass, lies somewhere ahead. Other scientists suggest more unusual goals, for example, quark stars. Though not quite black holes, hypothetical objects are denser than neutron stars. A sea of strange matter may form in these stars as a result of the neutron's extreme compression, which can cause their constituent quarks to split apart. Although they haven't been verified yet, physics doesn't rule them out. One already exists somewhere in the utter silence. Returning to your present course, mass still directs the stars you're getting closer to. Stephenson 218, the next giant, is a strange one. Although it has a larger volume than UI Scuti, if estimates are correct, its mass is likely to be less than 40 solar masses. It is not excessively heavy, but it is wide. This is a reminder that strength is not correlated with size. Most likely, this giant is a member of a star association, or cluster. About 19,000 light-years away from Earth is a loose cluster of red supergiants called Stephenson 2, or STI-2. A dense layer of interstellar dust partially blocks out the region's infrared glow. Astronomers look for thermal traces that shine through long wavelengths to see it. You consider how much of the universe is invisible, like heat through fog. Not because it's purposefully concealed, but rather because human eyes are only able to detect such a limited spectrum of light. Thankfully, your thoughts are unrestricted here, unlike when you listen to a song and hear just one instrument. You float through magnetic storms, gravity waves, X-ray bursts, and infrared ribbons. The vast, silent portrait is painted with a new brushstroke for every layer of the universe. You think about the silent reality that space teaches the best as the outline of Stephenson. 218 appears in front of you, still far away, and only a ghostly glow in the mist. The universe is balanced, not determined by appearances. You seem to be approaching the edge of something sacred as you drift more slowly now. You now know that stars wear masks made of their mass and size. The deepest mask yet lies ahead. Some stars are vast and fading, while others are bright and dense. You come upon a red, veiled hypergiant that is imperceptible but immeasurable due to its interstellar dust. You enter a field of mottled shadows as you cross the remaining expanse of open space. Fine grains of interstellar dust scatter and filter the light here, making it soft. Not because it isn't there. Stephenson 218 is a red hypergiant so massive that it is impossible to compare it to anything else in the universe. Its actual nature is obscured by distance and uncertainty. It is still more of a probability than a fully resolved object in our data. It is surrounded by a veil that is both literal and symbolic. Allegorical, in that many of its measurements are derived from indirect observations, and thick with cool gas and dust, rich in carbon. Nevertheless, the resulting image is astounding. About 19,500 light-years separate Earth and the star. Stephenson 218 is not just one of many stars in the constellation Scutum, which is a cradle of red supergiants and part of the enormous cluster known as Stephenson 2. With a radius more than 2,100 times that of our Sun, it might be the largest of all. If Stephenson 218 were used in place of the Sun, its photosphere would extend well past Saturn and might even touch Uranus's orbit. Slowly, you drifted in the direction of this omnipresent giant. Furthermore, its surface is still difficult to define. It is more presence than a point, more atmosphere than an object. Its outer layers are fragile. They resemble a fog rather than a skin. They escape into space, drift, and ripple. Because the density is so low, you could travel through the star's outer half without encountering any resistance, or even realizing that you were inside anything. Nevertheless, you float through its outer layer, submerged in a heated gas sea that is slowly churning. Around 3000 Kelvin and low pressure prevail here, but as the narrative progresses, things start to change. The heat intensifies, and the motion becomes more violent the farther you travel. The turbulence increases. It stirs in the fusion furnace. It is thought that Stephenson 218 is nearing the end of its life. It combines heavier elements in successive shells, after exhausting hydrogen in its core, just like UI Scuti. Every fusion layer resembles a nesting doll structure. The lifespans of hydrogen, helium, carbon, and oxygen are all shorter, deeper, and hotter. It will eventually develop an iron core, just like any other massive star, and gravity will prevail at that point. The balance is going to tip over in a split second. A supernova, an explosion that sends shock waves through the surrounding dust and gas, will result from the core imploding and the outer layers rebounding, causing new stars to emerge in its wake. It is the perfect way to end a stellar life, but occasionally something even more unusual happens. The pressure may surpass neutron degeneracy, the point at which even neutrons resist compression if the collapsing core is sufficiently massive. Completely, gravity prevails. Space encloses itself. A black hole is the result. Something so dense that light cannot escape. It is the quietest and most comprehensive triumph of gravity. You drift back towards the outer layers of this fictitious core. The gases are more diffuse and lighter here. Outward, solar winds blow steadily. These winds are strong in massive stars and remove mass at extraordinary speeds. A star may lose half or more of its mass over millions of years before it explodes. Iron will never be reached by fusion in lower mass stars like our Sun. A white dwarf will be left behind when it finally stops at helium and carbon, ejecting the outer layers in a gentle, luminous cloud known as a planetary nebula. In space, this dense cinder cools gradually. This balance is the source of all stellar fate diversity. For what length of time does fusion resist gravity? Nevertheless, you realize that no star endures forever. Fusion is a lovely pause in the collapse that forms all matter, but it is not a solution. And there wouldn't be any light without it. No warmth, not a single planet, no life. You sense the profound humility of that truth right now. All of your atoms, all of your breath, and everything you are were once contained in a star's fusion engine. It balanced, cooked, let go, and came back to the galaxy. A new star is forming somewhere. Another is fading elsewhere. You are right at home, resting in the space between them. The echo fills the pause between heartbeats. May you be held in the silence of the universe. May the slow rhythm of drifting lull you into sound, undisturbed sleep, and may the memory of the stars envelop you. Traveler, good night. Get enough sleep. Rest well. A star's power reverberates throughout the universe even after it dies. The extreme crushing of matter in neutron stars makes the impossible possible. Imagine looking into the cosmos and seeing a faint rhythmic pulse of light flickering like an invisible star's heartbeat. What could create such a bright, unrelenting pulse that defied space's silence? Greetings from the mystery of neutron stars. Our perception of reality is altered by the pulsing hearts of the universe, where the ashes of enormous stars beat with such ferocity. The mass of our Sun is contained within a sphere no wider than a city by these celestial remnants, which were created by apocalyptic explosions, and spin with a rhythm that reverberates across light years. Neutron stars invite us to explore an unfamiliar and breathtaking universe, challenging our understanding of physics, time, and existence itself, in ways that extend far beyond what is taught in textbooks. There is more to neutron stars than just astronomical curiosity. The laws of nature are pushed to their utmost in these cosmic laboratories. Imagine the center of a supernova, where a dying star collapses and crushes its core into a dense, energy-pulsing spinning orb. A neutron star is a celestial wonder with a density so high that 1 teaspoon of its material would weigh as much as Mount Everest. This is not your typical star. Its smoother-than-glass surface conceals a core where matter can dissolve into exotic and strange forms. These stars do more than shine. They emit beams of radiation that we detect on Earth as regular pulses, much like a lighthouse sweeping the universe. Why are we drawn to these pulses, encoded in a heartbeat that has traveled millions of years to reach our telescope? This exploration of neutron stars is an intellectual and temporal journey. This voyage will uncover mysteries that educational establishments have not yet investigated. From ancient stargazers who saw their explosive births to the scientists who deciphered their rhythmic signals, we will start by charting the historical quest to comprehend these cosmic hearts. The science behind their extraordinary nature will then be covered, including how their magnetic fields rival 1 trillion refrigerator magnets, how their enormous gravity distorts time, and how they create the gold in your jewelry. We'll discuss recent findings, including theories about alien matter hiding in their cores and waves rippling through space-time. We'll conclude by considering what these beating hearts reveal about our place in the vast, interconnected universe. The pulse of a neutron star is more than just a signal. It is a mirror reflecting the most profound truths of the universe. But why should we give a strange, far-off star any attention? Relics are not all that neutron stars are. They are the answers to the questions that plague us. What is produced when stars die, and how do they pass away? Is it possible for matter to exist in unimaginable forms? Could these cosmic hearts reveal the origin of the universe or its ultimate destiny? We are not merely observing as we stand on Earth and look at their weak pulses. Instead, we are communicating with a force that creates reality. The pulse of a neutron star serves as a poignant reminder that the universe harbors many mysteries and a call to wonder. Let us pursue this beating heart, this luminous cadence, and uncover what is beyond the classroom, deep within the throbbing core of the universe. Ancient stargazers stood beneath a glittering sky, their eyes catching brief bursts of light from far-off cataclysms, long before telescopes pierced the heavens. Could they have guessed that these flaming displays were the cry of birth for neutron stars, the throbbing, beating hearts of the universe? A guest star that was so bright it shone in daylight for weeks was discovered by Chinese astronomers thousands of years ago in the constellation Taurus. They had no idea that this was the supernova of the Crab Nebula, a stellar explosion that created a neutron star whose pulse we can still feel today. Throughout history, this cosmic pulse, a rhythm of radiant energy, has guided inquisitive minds to solve a mystery that school books hardly touched. Let's take a trip back in time to discover how people first became aware of the universe's deep significance after hearing its pulse. An English cleric named John Michell considered a radical idea during the 18th century as astronomers charted the stars. What if light couldn't escape a star because of its immense gravity? Too strange for his time, his dark stars were a faint whisper of neutron stars. Fritz Zwicky and Walter Baade examined the universe in the 1930s and proposed that supernovae left behind dense cores. Imagining a stellar corpse where matter was crushed into a nearly infinite density, they named these neutron stars. The faint pulse of a cosmic heart, too weak for the technology of their era, was like tuning a radio to pick it up. However, their audacious theory paved the way for a finding that would upend astronomy as we know it. Jocelyn Bell Burnell, a young graduate student, was bent over a radio telescope in Cambridge, England, in 1967, sorting through reams of data. As accurate as a metronome, she detected an odd regular blip every 1.33 seconds amid the static. Her team initially called it LGM1, half joking that it might be a signal from a little green man. However, this broadcast was not from space. Like a cosmic lighthouse, it was the pulse of a neutron star, a pulsar spinning wildly and emitting radio waves. Bell Burnell's discovery, which revealed the world's first observation of a neutron star's pulse, was a significant achievement. One of the first to confirm its fast pulse, a sign of a star's violent demise, was the Crab Pulsar, that old October guest star. Despite being initially passed over for a Nobel Prize, her work sparked a new wave of space exploration. From early skywatchers to Bell Burnell's discovery, these historical turning points are like reflections in the cosmic mirror, each catching a glimpse of the throbbing heart of the neutron star. They demonstrate how determined humans are to interpret the universe's signals, even when the instruments are crude and the concepts are fantastical. Bell Burnell's blips, Zwicky's dense cores, and Michael's dark stars were all steps towards solving a celestial mystery. With their unrelenting rhythms, neutron stars were real, not merely theoretical wonders. Their heartbeats reverberate throughout the universe like a drum beat. As we proceed, we'll delve into the science underlying these remarkable objects, examining how their heartbeat influences the universe and what mysteries it may have for us now. Imagine the surface of a city-sized sphere pulsing like the unrelenting heartbeat of a cosmic heart, as it rotates hundreds of times per second. How can the pulsing core of the universe, a neutron star, defy our shared sense of time and matter? Not all of these stellar remnants are dead stars. Gravity, magnetism, and quantum forces collide in these harsh labs in ways that textbooks never venture to investigate. Neutron stars, which are created when massive stars collapse in flames, contain the mass of the Sun in a ball that is only 20 kilometers across. Their densities are so great that one sugar cube of their material would be more than all of humanity on Earth. From their crushing gravity to their role as cosmic alchemists, creating the heaviest elements in the universe, let's explore the science behind their remarkable nature. Consider packing an ocean liner into a thimble, which is equivalent to a neutron star's density. Its core might become exotic matter, a soup of quarks unbound from regular atoms, after being crushed by unfathomable pressure. Space-time is distorted by this density, which slows time and bends light. Your watch would tick more slowly than it would on Earth if you were standing on the surface of a neutron star, which is impossible. Time dilation is a phenomenon peculiar to Einstein's theory of relativity. To a distant observer, a minute there might seem like hours, as though the pulse of the cosmic heart stretched the fabric of reality. Because of this intense gravity, even mountains that are smoother than a pool ball on the surface of a neutron star are only millimeters high due to the weight of the star. However, the speed at which this small orb spins is dizzying. Radiation beams from some pulsars that spin 700 times per second are faster than a kitchen blender and travel across space like the glow of a lighthouse. These beams are powered by magnetic fields that are 1 trillion times stronger than those of Earth. The force of these beams could destroy a spaceship. The pulses Jocelyn Bell Burnell detected are produced when a neutron star's magnetic poles misalign with its spin, causing it to emit radio waves, X-rays, or gamma rays. These pulsars serve as cosmic clocks. Astronomers can map the galaxy or test the theory of relativity thanks to their incredibly accurate pulses, which are comparable to those of atomic clocks. However, neutron stars are not just pulse stars. They create elements like silver and gold. Rapid neutron capture produces heavy elements during a supernova. Neutron stars spew treasures into space when they collide, as was the case with the gravitational wave event in February. Imagine a celestial forge sculpting the wealth of the universe, the cosmic heart pumping not blood, but the raw materials of planets and jewelry. Neutron stars conceal secrets beneath their surface. Strange states of matter, like quark-gluon plasma, where protons and neutrons dissolve, might exist in their cores. According to some theories, superfluids flow frictionlessly, causing the star's heart to dance without friction. These circumstances test our comprehension of quantum mechanics and push the boundaries of physics. Cosmic dynamos are also neutron stars. For millennia, the energy produced by their spins surpasses that of the sun. Modern research is removing these layers, revealing how these beating hearts move through space and time, and exposing the deepest mysteries of the universe, all of which are contained in their constant bright pulse, as we'll see in the following section. As its bright beats reverberate through contemporary telescopes, what mysteries does the throbbing heart of the universe whisper to us today? The city-sized remnants of stellar explosions known as neutron stars are no longer merely far-off oddities. They are celestial lights that shed light on the universe's deepest secrets. From gravitational waves generated by their collisions to exotic matter hidden in their cores, astronomers have recently captured their pulses in unprecedented detail. Understanding matter, space, time, and even our technological future is made possible by these discoveries, which go far beyond what is taught in the classroom. Let's examine how the unrelenting pulse of these stars resonates through state-of-the-art science, transforming our understanding of the universe and raising concerns about the future. In February 2017, the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected a cosmic symphony that reached Earth. Space-time trembled when two neutron stars locked in a death spiral collided 130 million light-years away. The confirmation that neutron star mergers create heavy elements like gold and uranium, as their pulsing hearts create a cosmic furnace, was made possible by this event, known as GW 170717. The afterglow, a brilliant flash of light, was captured by telescopes, demonstrating that these collisions illuminate the universe. A window into the extreme dance of gravity is provided by the radiant pulses of neutron stars, which, in contrast to black holes, leave visible scars. This discovery implied that the jewelry on your finger owes its existence to such apocalyptic embraces, connecting the beat of the cosmic heart to the formation of the very atoms in our world. However, what is inside the core of a neutron star? Exotic states of matter, like quark-gluon plasma, where protons and neutrons dissolve into a primordial soup, are suggested by modern theories. Imagine matter being compressed by the cosmic heart so violently that it resembles the state of the universe immediately following the Big Bang. Although neutron stars are natural laboratories, experiments such as those conducted at CERN's Large Hadron Collider seek to reproduce these conditions. Beyond our reach, their pulses contain hints about physics. Unusual quark matter, a stable state denser than nuclear matter, is hypothesized by some, while others propose that superfluids swirl in their cores and flow frictionlessly. With each beat of the cosmic heart providing a testbed for theories that could entirely alter our perception of reality, these concepts push the boundaries of quantum mechanics. Neutron stars also spark dreams of technology. They could serve as cosmic lighthouses for future spacecraft, guiding interstellar navigation with their precise pulses that rival atomic clocks. Ideas for utilizing the radiant energy of magnetars, neutron stars with powerful magnetic fields, have been sparked by their hint at energy sources that dwarf nuclear power. If the cores of neutron stars contain extraterrestrial matter, then this poses a philosophical conundrum. How does this affect our position in the universe? Do we resemble neutron star pulses, which are transient signals in an infinite universe? Picture yourself floating through the vastness of space in silence. A galaxy is a bright whirlpool of billions of stars, gases, and dust that revolves in front of you. Encircled by spiraling arms that resemble cosmic ribbons, the core glows brilliantly. Held together by an unfathomably powerful gravitational pull, it's a captivating dance of light and motion. However, a mystery lies concealed within this breathtaking display. Only a small portion of the mass required to maintain this complex ballet is made up of the galaxy's visible components, such as stars, planets, and nebulae. These celestial bodies are held together by what? What unseen force keeps the galaxy's whirling arms from breaking apart? This is the enigma surrounding dark matter, the universe's invisible structure. It is invisible to conventional telescopes because it doesn't emit light or energy, but its gravitational pull shapes clusters, galaxies, and the universe as a whole. It serves as the framework for the universe. When astronomers noticed discrepancies between what they could see and how galaxies behaved, the concept of dark matter emerged. Swiss astrophysicist Fritz Zwicky noticed in the 1930s that galaxies in the Coma cluster were traveling more quickly than they should have. He determined that visible matter by itself couldn't produce enough gravity to keep the cluster together using Newtonian physics. The required gravitational glue had to be provided by some missing mass. Kent Ford and Vera Rubin verified this phenomenon within individual galaxies decades later. They made an astounding discovery while examining the rotation curves of spiral galaxies. The speed of stars on galaxies' periphery was equal to that of stars close to the center. This was impossible under the laws of gravity unless there was an invisible mass that extended well beyond the boundaries. Our understanding of the universe has changed as a result of the discovery that the majority of its mass is invisible. According to current estimates, dark matter accounts for approximately 27% of the universe, which is significantly larger than the 5% that ordinary matter comprises. Dark energy makes up the remainder, which is even more enigmatic. Dark matter's invisibility paves the way for one of science's most ambitious projects. It is a puzzle that pushes the limits of our understanding and compels us to examine the structure of reality more closely. What is this invisible power? What is its relationship to the visible universe? And how does its presence affect our comprehension of life? The search for dark matter is about discovering the fundamental truths of the universe, not just solving an abstract puzzle. It includes existence and everything in between. The formation of galaxies, the reasons behind the universe's expansion, and possibly even a glimpse of the forces that shape the cosmos in its early stages, could all be revealed if we can comprehend this invisible force. This invisible force is shaping our universe. It envelops, penetrates, and sustains the universe. To comprehend dark matter is to understand the cosmos. Thus, the search starts with inquiries as deep and wide-ranging as the galaxies whirling in the night sky. Scientists use the faint traces left by invisible objects to detect their presence. The phenomenon of gravitational lensing, a remarkable byproduct of Einstein's general relativity theory, provides one of the strongest indirect arguments for the existence of dark matter. When light from a more distant source is bent by the gravity of a massive object, like a galaxy or a cluster of galaxies, this phenomenon is known as gravitational lensing. Like a glass lens, this bending produces distorted, magnified, or even multiple images of the background object. Astronomers discover something strange when they gauge the extent of this lensing. The galaxy or cluster's visible mass is much too small to explain the extent of light bending. These effects require a tremendous gravitational pull that is far stronger than what could be produced by observable matter. This disparity implies that these galaxies are surrounded and penetrated by an invisible mass. Despite being invisible, dark matter has a gravitational pull that manifests itself through these cosmic distortions, enabling astronomers to observe its effects even in the absence of direct matter observation. The rotation curves of galaxies provide yet another critical piece of evidence for dark matter. Graphs that display the speed of gas and stars about their separation from the galactic center. The stars farther from the center of a galaxy, with only visible matter, should orbit more slowly, much like the planets in our solar system. This is because the mass that generates the gravitational pull primarily resides in the dense, star-filled core, and gravity decreases in strength as the distance increases. Observations, however, paint a very different picture. Even when stars in spiral galaxies were located far from the galactic center, Vera Rubin and her colleagues discovered that their rotational velocities stayed relatively constant. This flat rotation curve suggests that there is a massive, invisible halo of mass that extends far beyond the visible stars. The stars at the galaxy's periphery should be hurled into space in the absence of this invisible matter, because they can't sustain their high speeds. It makes sense to conclude that the galaxy is surrounded by a massive halo of dark matter, which provides the gravitational pull required to stabilize the outer stars. Galaxy rotation curves and gravitational lensing both demonstrate the ubiquity of dark matter in the universe. When combined, they create a coherent story. The universe is far more complex than it initially appears. Dark matter affects entire clusters of galaxies, not just individual ones. Studies of massive galaxy clusters using gravitational lensing provide detailed maps of the distribution of dark matter, demonstrating how it gathers in giant structures that serve as the universe's scaffolding. Like individual galaxies, these clusters are stabilized by the massive gravitational pull of dark matter. These oblique observations demonstrate the inventive nature of science. Because dark matter cannot be seen or directly interacted with, scientists must rely on its gravitational footprints to determine its existence. Every warped picture and surprising star velocity is a clue that helps us learn more about the invisible. These pieces of evidence prove the existence of dark matter beyond a reasonable doubt, even though its nature is still unknown. Dark matter is a real phenomenon, not just a theoretical concept. This palpable force is shaping the universe. Despite its indirect detection, its influence on the universe cannot be denied. Because it is invisible and interacts with normal matter only weakly, if at all, dark matter remains a mysterious concept. Due to this, direct detection is challenging and requires experiments with unmatched sensitivity and accuracy. Despite these obstacles, researchers have developed creative techniques and state-of-the-art facilities to attempt something that might seem unattainable: directly capturing evidence of dark matter. The Large Hadron Collider smashes particles to solve mysteries. The most powerful particle accelerator in the world is the Large Hadron Collider, LHC, housed at CERN in Geneva. The LHC, which has a 27-kilometer ring buried underground, creates conditions akin to those that existed immediately after the Big Bang by smashing protons together at nearly the speed of light. Detectors carefully examine the particles produced by these high-energy collisions to look for anomalies, which could be signs of dark matter. Weakly interacting massive particles, or WIMPs, are a prime candidate for dark matter that scientists at the LHC are particularly interested in discovering. According to the theory, WIMPs could be produced during these collisions. Like neutrinos, WIMPs might show up as missing energy in the data that escapes the detectors without interacting. Although the LHC hasn't yet produced concrete proof of dark matter, the experiments have yielded applicable limitations that have narrowed the range of potential characteristics that dark matter might possess. In an effort to find dark matter particles among the debris of their high-energy collisions, scientists are continuing their search with improved detectors and adjusted collision parameters. The large underground xenon LUX detector, one of the most sensitive devices ever constructed to search for dark matter, is situated deep underground in the Sanford Underground Research Facility in South Dakota, protected from cosmic rays and other background noise. LUX detects the smallest interactions between dark matter particles and normal matter using a tank full of ultra-pure liquid xenon. It's a simple but ambitious principle. A tiny ionization signal and a tiny burst of light scintillation will be produced if a dark matter ultra-sensitive photomultiplier tubes, which can pick up even the slightest hints of activity, then record these signals. Despite LUX not yet detecting conclusive proof of dark matter, its findings have raised the bar for sensitivity and helped rule out specific theoretical models of dark matter. Even more sophisticated is its successor, the Lux Zeppelin LZ, which features a larger detector and enhanced capabilities for searching for the elusive presence of dark matter in cosmic silence. The search for dark matter involves many other experiments in addition to the LHC and LUX. To increase the likelihood of detection, projects such as Xenon 1T in Italy, PICO in Canada, and SuperCDMS in the US employ a range of techniques, including bubble chambers and cryogenic detectors. Each of these experiments addresses a distinct piece of the dark matter puzzle, demonstrating the international cooperation and interdisciplinary creativity needed to address this significant issue. The variety of approaches ensures that even if one approach is unsuccessful, others may be able to reveal the mysteries of dark matter. A turning point in physics would be reached if dark matter were directly discovered, proving the existence of a hitherto unseen aspect of the cosmos. It would open up entirely new areas of knowledge, in addition to providing answers to long-standing queries. The fact that the search is still ongoing is evidence of humanity's unwavering curiosity and will to uncover the invisible forces that shape the universe. One of the most significant problems facing modern physics is the detection of dark matter. Dark matter is, by definition, impossible to observe directly. It doesn't interact with electromagnetic forces, or emit, absorb, or reflect light. Its presence can only be inferred by its gravitational pull, so the search is like chasing shadows in a dark room. These challenges haven't stopped scientists, though. Instead, they have stimulated creativity, expanding the frontiers of theoretical physics and technology. According to the dominant theory, the weak nuclear force and gravity are the primary means by which dark matter interacts with ordinary matter. If this is accurate, then dark matter particles are virtually undetectable as they move through ordinary matter. For comparison, imagine that billions of dark matter particles could be passing through your body undetected right now. Due to this weak interaction, extremely sensitive detectors are necessary. Cosmic rays, neutrinos, and even Earth's natural radioactivity are among the background noise that these instruments must separate from any possible dark matter signals. To reduce interference, researchers frequently set up their experiments in isolated areas or deep underground. Advanced technology is needed to search for dark matter, but this comes at a high cost. Substantial financial and logistical support is required for facilities like the Large Hadron Collider and underground detectors such as LX or Xenon. Furthermore, due to the extreme complexity of these instruments, Even minor malfunctions can cause delays of months or even years in research. Liquid xenon detectors, for example, must be kept extremely pure to prevent contamination that could mimic dark matter interactions. To achieve this level of accuracy, each experiment necessitates a delicate balance between creativity and pragmatism. The ambiguity surrounding the nature of dark matter is one of the biggest obstacles in the search for it. The discussion is dominated by theories, such as WIMPs, weakly interacting massive particles. But there are competing possibilities from axions, sterile neutrinos, and primordial black holes. Resources and efforts must be divided, because each theory calls for a different experimental strategy. Furthermore, scientists might be looking in the wrong place if dark matter does not fit into these pre-existing models. It's still possible that dark matter interacts through unidentified forces, or is composed of particles that don't fit the standard model of physics, which forces scientists to rethink their presumptions constantly. The universe's dark matter is not dispersed equally. Although its density varies greatly depending on location, it clusters in halos surrounding galaxies and galaxy clusters. On Earth, finding dark matter is like trying to find a grain of sand in a desert. Probability and scale are problematic. This unequal distribution further complicates the timing of the experiment. In specific experiments, changes in dark matter and particle flux are detected by tracking the Earth's movement through the galaxy. It takes years of data collection to confirm the existence of such seasonal or directional signals, because they are so weak. The hunt for dark matter continues, despite these enormous obstacles. Every unsuccessful experiment yields essential information that helps us focus on the issue and reduce the range of potential solutions. In the scientific process that leads to a final breakthrough, these small steps are crucial. Thousands of scientists, engineers, and theorists from various fields are cooperating in the global search for dark matter. The limits of sensitivity are about to be pushed further by new experiments, like the Lux-Zeppelin LZ detector and improvements in neutrino observatories. In the meantime, theoretical physicists continue to develop models that incorporate dark matter into the broader framework of cosmic evolution, offering new insights and potential detection pathways. The stakes are very high. The discovery of dark matter would transform our knowledge of the cosmos in addition to confirming its existence. It might shed light on the mechanisms that formed galaxies, offering clues about the early universe and demonstrating links between the microscopic world of particles and the macroscopic structure of the universe. More than anything else, the search for dark matter embodies the spirit of human inquiry. It demonstrates our desire to learn about the invisible, to discover the forces that hold the universe together, and to push the limits of our current understanding. One of the most effective scientific theories is the standard model of particle physics. The fundamental particles, such as quarks, leptons, and bosons, as well as the forces governing their interactions, are described. This encompasses the weak, strong, and electromagnetic nuclear forces. The standard model provided a logical explanation for a large portion of the observable universe after the Higgs boson was discovered in 2012. One obvious issue, however, is that the standard model does not account for dark matter. Although it gracefully describes how ordinary matter behaves, it overlooks the enigmatic material that comprises approximately 27% of the universe's mass-energy content. Due to this disparity, the standard model is under tremendous strain, compelling researchers to seek additions or entirely different frameworks. The gravitational effects of dark matter are one of the most obvious ways it contradicts particle physics. No particle in the standard model can generate the enormous gravitational pull that dark matter is thought to provide. In the past, neutrinos, the only electrically neutral, weakly interacting particles in the standard model, were thought to be promising. They cannot, however, account for the observed behavior of galaxies and galaxy clusters due to their small masses and high velocities. The gravitational pull of dark matter suggests that it must be composed of a novel type of particle with sufficient mass to influence the universe, yet with weak interactions with regular matter. This criterion compels researchers to seek solutions beyond the conventional model. Because dark matter appears to be unaffected by electromagnetic forces, it remains invisible. Since it neither emits, absorbs, nor reflects light, it cannot be detected using conventional techniques. Due to this characteristic, it is not classified as a particle essential to the standard model, such as electrons or photons. The nature of dark matter is seriously called into question by the lack of electromagnetic interaction. Does it fall under a completely different category of particles? Does it use unidentified forces to interact? These possibilities suggest that there is more to physics than the current paradigm, necessitating new theoretical approaches. The existence of dark matter raises questions about the accuracy of the standard model. Supersymmetry and SuSi are two theories that try to close this gap. By suggesting a partner particle for every known particle, this theoretical framework expands upon the conventional model. In this regard, a neutralino, the lightest supersymmetric particle, or LSP, is a viable dark matter candidate. However, this theory has been called into question due to the inability of experiments, such as the Large Hadron Collider, to detect supersymmetric particles, sectors that are hidden. According to specific models, dark matter exists in a hidden industry, a parallel universe of forces and particles that only weakly interact with ordinary matter through gravity. According to this theory, exotic particles such as sterile neutrinos and axions could be candidates for dark matter and modified gravity. Some physicists investigate the possibility that our understanding of gravity itself may be incomplete, even though it is not a particle-based phenomenon. Among these theories is modified Newtonian dynamics. By arguing that gravity acts differently on cosmic scales, Mond questioned the necessity of dark matter. These theories, however, struggle to match the data that phenomena like gravitational lensing provide. The standard model is not the only thing that dark matter challenges. It provides access to unexplored areas. The discovery of dark matter particles has the potential to fundamentally alter our knowledge of the forces governing the universe, its evolution, and the fundamental structure of reality. A discovery of this kind could bring together various branches of physics, from the quantum scale to cosmological structures, and provide answers to long-standing questions, such as the nature of gravity and the origins of the universe. WIMPs, or weakly interacting massive particles, are the most prominent of the many theories put forth to explain dark matter. WIMPs are hypothetical particles that are predicted to have masses significantly larger than protons, but only weakly interact with regular matter. They can, therefore, travel through planets, stars, and even human bodies without being detected. WIMPs are attractive because they support the theory of thermal relics. High-energy interactions produced and destroyed particles in the early universe. Some of these particles survived, but the majority decayed or were destroyed as the universe cooled and expanded. WIMPs are a strong contender for the dark matter component because their predicted abundance closely matches the observed density of dark matter. The axion, a hypothetical particle that is far lighter than WIMPs, is another intriguing candidate for dark matter. In the standard model, axions are a solution to theoretical issues. In particular, the behavior of quarks and gluons in quantum chromodynamics, QCD, is the subject of the strong CP problem. Axions are incredibly light and have very weak interactions with radiation and matter, in contrast to WIMPs. The ability of axions to create a massive, imperceptible field that pervades the universe is what makes them so intriguing. The observed rotation curves of galaxies and other gravitational phenomena ascribed to dark matter may also be explained by these particles. To find axons, ongoing experiments such as the Axion Dark Matter Experiment, ADMX, search for their anticipated interaction with electromagnetic fields. Sterile neutrinos are an enigmatic variant. Although they differ significantly, sterile neutrinos are an extension of the neutrinos found in the Standard Model. Other than gravity, none of the known forces cause them to interact. If they were created in sufficient quantities in the early universe, these heavier, sterile counterparts of regular neutrinos might make up dark matter. The decay of sterile neutrinos may produce detectable X-rays, which makes them interesting. Though there is currently no conclusive evidence, interest in this candidate has been stoked by observations of unexplained X-ray emissions from galaxies and galaxy clusters. Dark matter, which lacks particles, is represented by primordial black holes. Primordial black holes, or PBHs, are a less common candidate for dark matter. PBHs are compact objects that may have formed soon after the Big Bang, in contrast to particle-based explanations. These black holes could make up at least some of the dark matter in the universe and range in size from microscopic to many times the mass of the Sun. Even though exotic new particles are not needed for PBH, their existence would have a significant impact on our knowledge of the early universe and cosmology. To determine if PBHs can account for the observed effects of dark matter, researchers are currently investigating cosmic background radiation and gravitational lensing. The variety of dark matter contenders is indicative of the difficulty of the task. Researchers investigate alternative theories, such as superfluid dark matter, which postulates that dark matter may form a quantum superfluid that has distinct effects on gravity, in addition to WIMPs, axions, sterile neutrinos, and primordial black holes. Extremely light particles with wave-like characteristics make up fuzzy dark matter, which has the potential to form large-scale structures. Some galactic phenomena may be explained by self-interacting dark matter, which is composed of particles that interact with themselves, but not with ordinary matter. Every contender stands for a distinct aspect of the dark matter conundrum. Axions and sterile neutrinos push the limits of particle physics, while WIMPs dominate underground and collider detection efforts. The idea that dark matter exists at all is called into question by exotic theories and the possibility of primordial black holes. The search demonstrates the scientific community's inventiveness and flexibility for these candidates. The discovery of dark matter will fundamentally alter our knowledge of the universe and its governing principles, regardless of whether it proves to be a familiar particle or something completely unexpected. The discovery of dark matter would fundamentally alter our understanding of the universe's structure and history. Currently, dark matter is believed to be the unseen framework upon which galaxies and other cosmic structures are constructed. Determining its nature would allow us to provide basic answers regarding the creation, development, and current state of the universe. Dark matter played a crucial role in forming the cosmic web in the early universe, shortly after the Big Bang. Dark matter is unaffected by electromagnetic forces and can clump together under the influence of gravity, whereas ordinary matter interacts with light and radiation. As gravitational wells, these clusters drew in regular matter, creating the seeds that would become the galaxies. By learning more about the characteristics of dark matter, we could improve our models of these early processes and get a better understanding of how planets, stars, and galaxies formed. A vast interconnected network of galaxies, clusters, and voids makes up the structure of the universe. The gravitational pull of dark matter shapes this cosmic web. These structures would not exist as we see them today without it. Scientists could more accurately model the large-scale evolution of the universe if they could determine the characteristics of dark matter, such as its mass, interaction strength, and particle behavior. These discoveries would fill in knowledge gaps about how cosmic structures evolved over billions of years, and how dark matter and dark energy continue to shape them. The role of dark matter is not confined to the past. The future is also shaped by it. The expanding force of dark energy, which propels the universe's continuous expansion, is opposed by the gravitational pull of dark matter. Predicting the ultimate destiny of the universe is easier with an understanding of the balance between these forces. The universe may either contract in a big crunch or continue to expand indefinitely, eventually freezing in a heat death, depending on how dark matter interacts. On the other hand, if dark matter deteriorates over cosmic timescales, dark energy may take over and accelerate even faster, causing a large rip. Physicists could improve these scenarios and provide significant insights into the future of the universe by locating and examining dark matter. The quantum and the cosmic, two seemingly unrelated branches of physics, would be brought together by the discovery of dark matter. Dark matter most likely consists of particles that obey the laws of quantum mechanics at its core. On the largest scales, however, it has an impact that shapes galaxies and the universe. Scientific advances in other fields, like particle physics and the identification of dark matter, could result from this connection. The standard model may be extended if particles uncover new forces or symmetries in the natural world. Astrophysics' understanding of dark matter will improve models of black hole behavior, galaxy dynamics, and star formation. Understanding dark matter in cosmology may help us comprehend inflation and other processes that occurred near the Big Bang, providing insights into the early history of the universe. Beyond the obvious scientific ramifications, the discovery of dark matter would have a profound impact on humanity's understanding of its place in the universe. It demonstrates that a large portion of the universe is composed of a material that is distinct from the matter that makes up our planet, our bodies, and everything else we have ever encountered. By highlighting the fact that we are a part of a far greater and more profound whole, this insight can strengthen our sense of connection to the universe. The discovery of dark matter may have fascinating ramifications. Every significant scientific advance in the past has produced surprising findings. Modern technology was made possible by electricity, and quantum mechanics completely changed how we think about the cosmos. Gaining insight into dark matter may reveal previously unimaginable physical forces or phenomena. In this way, discovering dark matter is about more than just unraveling a mystery. It's about pushing the limits of human understanding, exploring uncharted territory, and finding facts that may completely alter how we perceive the universe. In cosmology, the study of the universe's formation, development, and structure, dark matter is essential. The foundation of cosmic structures, its gravitational pull, determines how galaxies form, cluster, and change over billions of years. The universe as we know it would not exist without dark matter. Therefore, improving our models of the universe's formation and large-scale behavior requires an understanding of dark matter. Dark matter began to group under the force of gravity in the early universe immediately after the Big Bang, creating dense areas that served as seeds for future galaxies. The galaxies and clusters we see today were formed when ordinary matter, which is made up of atoms, fell into these dark matter wells after first being scattered by intense radiation. This process would have been impossible to complete without dark matter, leaving the universe essentially unstructured. Deciphering these early cosmic events requires investigating dark matter. Edwin Hubble made the initial discovery that the universe was expanding in the 1920s. This expansion has accelerated over time due to an enigmatic force called dark energy. Together, Dark matter and dark energy make up about 95% of the universe's mass-energy composition. The dynamics of the universe are shaped by their interaction. Through its gravitational pull, dark matter slows the expansion, but dark energy accelerates it in the opposite direction. Deciphering this delicate balance requires an understanding of dark matter. The interaction between dark matter and dark energy influences the rate of cosmic expansion. Cosmologists would be able to forecast the future course of the universe more precisely if they had a better understanding of the characteristics, density distributions, and interactions of dark matter. The universe's ultimate destiny is still unknown. The role and behavior of dark matter over cosmic timescales will largely determine whether the universe ends in a big freeze, a big crunch, or a big rip. In cosmology, the lambda-cold dark matter, LCDM model, is the dominant paradigm. It depicts a universe made up of ordinary matter, and dark energy. Although lambda-cold dark matter has been practical in explaining observations such as large-scale galaxy distributions and cosmic microwave background radiation, it remains insufficient in the absence of a more comprehensive understanding of dark matter. Assumptions regarding the characteristics of dark matter are crucial to the formation of structures and simulations of galaxy and cluster formation. A deeper comprehension could address minor-scale anomalies and differences between the distributions of simulated and observed galaxies. Some small-scale phenomena, like the observed density profiles of dark matter in galaxies, are complex for the lambda-cold dark matter model to explain. The cusp core problem still exists. These discrepancies might be resolved by a more thorough comprehension of dark matter. Investigating dark matter could also reveal details about the universe's early history. The behavior of dark matter during this epoch could provide insights into the inflationary era, the rapid expansion of the universe immediately following the Big Bang, baryogenesis, the process by which ordinary matter came to dominate over antimatter, and Ryanization, the time when the first stars and galaxies formed. Conditions were so extreme shortly after the Big Bang that matter and energy were indistinguishable. By linking the characteristics of dark matter to these occurrences, cosmologists could Ryanize the neutral hydrogen in the universe and close gaps in our knowledge of the early stages of the universe. Studying dark matter has significant implications for understanding dark energy, the mysterious force driving cosmic acceleration. Despite their differences, these two phenomena have a profound impact on the universe's destiny. To provide a more comprehensive understanding of the universe's mass and energy content, as well as its ultimate fate, research into dark matter may uncover new physics that unifies these concepts. Similar to Einstein's general theory of relativity or Copernicus's heliocentric model, an understanding of dark matter would represent a paradigm shift in cosmology. It would uncover the fundamental mechanisms governing the universe and improve our understanding of its expansion. We get one step closer to answering the bigger questions by addressing the dark matter question. From where did we originate? The discovery of dark matter would be a pivotal moment in particle physics, marking the beginning of fields of study that extend far beyond the conventional model of particle physics. Although the standard model has done a remarkable job of explaining the known forces and particles, it is unable to explain the enigmatic material that constitutes 27% of the universe. This apparent discrepancy raises the possibility of entirely new particle forces or symmetries that go beyond what we currently know about the universe. Discovering the true nature of dark matter could fundamentally alter our understanding of the subatomic world if it is composed of particles. Weakly interacting massive particles, or WIMPs, are among the most promising approaches to this problem. WIMPs would be the front runners for a new class of particles interacting through weak nuclear forces. Their discovery may lead to the discovery of new interactions and extensions of the Standard Model, including supersymmetry, which postulates that all known particles have their partner particles, known as axions. The strong CP problem in quantum chromodynamics and the dark matter mystery would be resolved with the discovery of axions. Axions may serve as a link between particle physics and cosmology, revealing previously undiscovered connections. Sterile neutrinos. Unlike their counterparts in the Standard Model, these hypothetical particles would only interact through gravity. Discovering sterile neutrinos could help us gain a deeper understanding of neutrino physics and provide insights into the behavior of other elusive particles. Every one of these particles can change our understanding of the world by revealing previously unknown relationships or aspects of it. In the context of dark sector physics, dark matter implies the existence of previously unidentified forces or interactions. According to some theories, particles similar to photons in the visible universe act as a medium for dark forces that cause dark matter to interact with itself. Finding evidence of these forces may reveal a dark sector that runs parallel to the observable universe, a completely new layer of reality. A fifth force of nature might be revealed in this way. Imagine unexpected interactions between dark matter and ordinary matter. Then, in addition to the four forces that are currently understood, gravitational, electromagnetic, strong nuclear and weak nuclear, it may allude to a new fundamental force. These findings bring disparate phenomena together under a more comprehensive theoretical framework, radically changing our understanding of how the universe functions. The potential for dark matter research to bridge the gap between general relativity and quantum mechanics is among its most significant ramifications. Theoretically, the two pillars of modern physics are still incompatible. Dark matter presents a unique chance to investigate phenomena that might bridge the gap between quantum and cosmic scales. The behavior of dark matter could provide insight into how quantum effects manifest at macroscopic gravitational scales if it is composed of quantum particles with wave-like characteristics. Gaining insight into the gravitational pull of dark matter may help us develop a theory of everything by providing hints about quantum gravity. Technological developments spurred by the search for dark matter have benefited particle physics in general. The Large Hadron Collider, LHC, and other high-energy experiments are continually being improved to achieve higher sensitivity, thereby opening the door to discoveries beyond the realm of dark matter. Other unsolved physics questions are already being investigated using advances in detector design, such as the use of ultra-pure materials and cryogenic processes. These developments enhance our ability to investigate phenomena such as neutrino oscillations, proton decay, and the asymmetry between matter and antimatter, as well as improve our capacity to detect dark matter. It would be necessary to expand the Standard Model to incorporate new particle interactions and symmetries to discover dark matter. Expanding the Standard Model could help us understand other cosmic mysteries, such as dark energy or the imbalance between matter and antimatter, provide insights into what happened in the early universe, including events during and after the Big Bang, and reveal connections between seemingly unrelated concepts like dark matter and the Higgs field. Research on dark matter would lead to advances in particle physics, with implications for various fields, including cosmology and astrophysics. These findings have the potential to reinterpret fundamental concepts such as mass and force, as well as the essence of reality itself. We will be able to respond to more in-depth inquiries about the nature of existence as our theoretical frameworks advance. One thing is very evident as we come to the end of this voyage through the invisible universe. One of the biggest mysteries of our day is dark matter. Its discovery and comprehension have the power to alter not just physics, but also how we view the world. Dark matter remains tantalizingly elusive, despite all that we've studied about it, including its gravitational fingerprints, the suspected particles it comprises, and its role in the universe's evolution. This mystery is a powerful reminder of how big the unknown is. We cannot yet fully comprehend the size, complexity, and wonder of the universe. Dark matter is only one component of a much bigger picture that also includes dark energy, the universe's beginnings, and the essence of life itself. The continuous investigation into dark matter is a testament to human ingenuity and curiosity. It embodies the finest of science, an unrelenting quest for understanding motivated by the conviction that the solutions are only a step away. We get one step closer to learning the secrets of the universe with every experiment, observation, and theoretical development. However, dark matter is both a source of inspiration and a scientific challenge. It challenges us to ponder what might be concealed within the universe's fabric, to dream, and to ask questions. What uncharted physics is waiting to be discovered? How will these realizations change the way we think about the universe and ourselves? Dark matter research has a bright future full of possibilities and promise. We are getting closer to direct detection thanks to technological advancements, such as next-generation particle accelerators and more sensitive detectors. The subtle effects of dark matter on galaxies and beyond will be revealed by new telescopes and space missions that will map the universe with previously unheard-of precision. In the meantime, theoretical physicists continue to push the envelope, investigating concepts that may seem unthinkable now, but could lead to breakthroughs in the future. Every advancement in the search for dark matter broadens our knowledge of the cosmos and serves as a reminder that learning is never fully attained. We will undoubtedly find new questions, new frontiers to explore, new challenges to overcome, and new wonders to marvel at as we unravel the truth about this puzzle. Therefore, let's welcome the mystery of dark matter as we look to the future. Let it remind you that there are countless things in the universe waiting to be discovered. Although there is still much to learn about dark matter, each step we take advances our understanding of the fundamental questions surrounding the universe's existence. What constitutes the universe? From where did it originate? What role do we play in it? Ultimately, the simplest yet most profound realizations often lead to the most significant discoveries. The most significant source of wonder is the universe's inherent mystery, which is far more profound than we could have ever imagined. Have you ever considered the possibility that there are other realities besides your own? What happens if there is another one out there? Are you making different decisions, pursuing other dreams, and leading an entirely different life? Could this situation occur, or is it merely a thought experiment? How does that alter everything we know about life if it is? We will explore the philosophy and science of parallel universes on this trip. This concept is so vast and mysterious that it profoundly alters our perception of the world. Imagine that there is a different version of you out there, far beyond our range of vision. You are more than one version of yourself. You might be an explorer mapping the unknown in one reality, and an artist producing amazing works of art in another. It has a science fiction-like sound. What if it's more than a story, though? What if the possibility of parallel universes is ingrained in the structure of our universe, rather than being a work of fiction? We have thought for centuries that there is only one reality, one timeline, one set of events, and one you. The idea of parallel universes, however, completely contradicts that notion. It implies that reality is an infinite web with countless possibilities developing concurrently rather than a single thread. Imagine flipping a coin and seeing if it is heads or tails. Now, consider a scenario in which both of these outcomes take place in different universes. It's difficult for us to comprehend. The real question, though, is this: where are these universes if they exist? Why can't we see, feel, or confirm their existence? What does it mean for us, for our comprehension of life itself, if they are real? The concept is mind-bending. It forces us to re-evaluate our assumptions about the world. We must look to science to thoroughly investigate its depth, as some of the most astounding theories indicate that parallel universes may be more than a theory. Parallel universes. By that, what do we mean? Is it a vast celestial replica of our world, or is it something else entirely? In actuality, there isn't a single solution. There are several theories about parallel universes that have been investigated by philosophers and scientists alike, and each one is more intriguing than the others. Let's begin with a single concept: limitless potential. Consider every decision you've ever made, every path you've traveled, and every word you've ever said. Now picture all the decisions you didn't make, resulting in a different universe and reality where events went differently. You might have chosen to follow your childhood dream in one universe, while choosing a different course in another. Every choice opens a new chapter in an endless book, making it resemble a cosmic version of the choose your adventure narrative. The concept of alternate timelines comes next. Imagine history as a single thread that stretches across time. Imagine now that that thread branches out at significant historical junctures. What if dinosaurs had never been extinct in a different universe? What if humans had never discovered fire? Completely different timelines with unimaginable consequences may be developing alongside our own. Here's the twist, though. These interpretations go beyond simple philosophical reflections. Some of the most fascinating scientific theories give rise to them. According to quantum mechanics, for instance, every quantum event has the potential to divide reality into several possible outcomes. A particle travels to the left in one universe. It moves to the right in another. A logical investigation of this concept reveals a possibly infinite multiverse that arises from quantum unpredictability. What about the scale of the universe in the quantum world? According to some scientists, our universe is merely one bubble in a vast cosmic sea of bubbles. There are countless separate universes, each with its own set of physical laws. Picture yourself adrift in a sea where each bubble contains an entirely different world. Therefore, the interpretations of parallel universes are as varied as they are mind-bending, whether they involve infinite possibilities, alternate timelines, or entirely distinct universes. However, if these universes are real, is there a way for us to communicate with them or even establish their existence? What does the existence of parallel universes mean for us then? It is more than just a scientific conundrum. It's a question that challenges our fundamental beliefs about who we are and our place in the universe. First, let's discuss the philosophical ramifications. Who are you if reality exists in infinite versions? Are you merely a single manifestation of an endless array of options? The idea is deeply unnerving. Philosophers have been debating the concepts of identity, free will, and the meaning of life for centuries. However, the concept of parallel universes raises those issues to an entirely new level. Consider it. In one universe, a choice you make could result in extraordinary success. You could have a spectacular failure in another. Could your decisions be meaningless? Or does it imply that every decision matters because it shapes a different reality? Then, there is the issue of free will and fate. Does the existence of parallel universes imply that all possible versions of your life are already predestined and exist? Or are you still in charge of your fate, directing one course while others take shape in other places? This paradox challenges all our preconceived notions about how the universe operates and how we interact within it. Let's now turn our attention to the scientific implications. The concept of parallel universes is derived from some of the most advanced physics theories and is not merely philosophical conjecture. For instance, according to the many worlds interpretation of quantum mechanics, the universe splits into several parallel universes each time a quantum event occurs. The particle shifts to the left in one version. It moves to the right in another. This motion is not merely a theoretical exercise. It is a direct result of the behavior of quantum systems. There is also the theory of cosmic inflation, which is more expansive. This theory suggests that the vast expansion of space following the Big Bang may have produced countless other universes, including our own. Our universe might be a speck in an unimaginably large multiverse, with each universe having its own distinct set of physical laws. Here's the worst part, though. How can we demonstrate the existence of these parallel universes? They are, after all, outside the realm of our present knowledge and technology. However, researchers are still seeking hints, even small ones, in the distribution of galaxies, the patterns of the cosmic microwave background, or even phenomena that have yet to be discovered. What does it mean to be a part of a universe with limitless possibilities that we might never fully understand? Are we observers of one narrow thread, or explorers of a vast unknown? The ramifications are both profound and enigmatic, making us reevaluate not only what we already know, but also how we came to know it. Let's now explore the science, empirical data, and theories that help move the concept of parallel universes from fiction to the realm of physics. Quantum mechanics is the source of one of the most intriguing scientific theories regarding parallel universes, the area of physics that studies the smallest particles that make up the universe, particles such as photons and electrons. The universe doesn't behave as we're accustomed to at this microscopic level. Particles exist in a peculiar state of uncertainty rather than predictability. This is the exciting part. Hugh Everett, a physicist, put forth a radical theory called the many worlds interpretation in 1957. He proposed that the universe divides into two separate realities whenever a quantum event occurs, where a particle must choose between two states. Every possible result occurs, but in a distinct realm of reality. Consider it this way. At this crucial juncture, you must decide whether to turn left or right. If you turn left in one universe, you turn right in another, according to the many worlds interpretation. Both choices are actual. They take place in different realities. There is more to this theory than just choices. It has to do with everything. Each quantum decision produces a branching network of parallel universes with distinct paths. Every split creates a new reality, much like an endlessly growing tree. Here's the catch, though. We are unable to communicate with these universes if they exist. Like pages in a book, they are distinct and never meet. Because of this, interpreting the various worlds is both exciting and frustrating. Although it provides a fantastic explanation for quantum behavior, it raises doubts about whether we will ever be able to determine whether these other worlds are real. However, there are proponents of the theory. Although it also poses essential questions regarding the nature of reality, many physicists believe it provides answers to some of the most profound problems in quantum mechanics. What do we mean by reality if the universe is constantly dividing? And does that imply that nothing is unique, including you, if every possibility exists somewhere? The interpretation of the many worlds is only the first step. We will need to look beyond the quantum scale and into the vastness of the cosmos itself to learn even more about the science of parallel universes. Cosmic inflation reaches the largest scales of reality, the very beginnings of the universe itself, while the many worlds interpretation explores the most minor scales. This theory may suggest the existence of an infinite number of other universes, in addition to explaining how our universe came to be. What exactly is cosmic inflation, then? Imagine the cosmos as we know it, a huge region teeming with planets, stars, and galaxies. Go back in time now. Everything we see today was crammed into an unthinkably small, hot, and dense point some 13.8 billion years ago. Then, in a split second, an extraordinary event occurred. The expansion of the universe was swift and nearly explosive. Scientists refer to this as inflation. This is where it becomes interesting, though. Many physicists think that our universe wasn't created by this process alone. Instead, inflation could have been going on everywhere, generating innumerable bubble-like universes that grow and change on their own. Imagine bubbles forming, expanding, and rising to the surface of a pot of boiling water. Every bubble represents its universe, complete with distinct physical characteristics and its own set of natural laws. According to this theory, our universe might be one bubble in an endless multiverse, a huge cosmic vast where expansions form and vanish. This is where some of these universes get bizarre. The laws of physics are entirely different. There might be more gravity, stars may never form, or life changes in ways that are beyond our comprehension. There is more to the theory of a multiverse arising from cosmic inflation than meets the eye. Some researchers are currently seeking evidence. For example, the cosmic microwave background, the faint glow of radiation left over from the Big Bang, could have subtle imprints if our universe had ever collided with another bubble universe in the distant past. Nevertheless, cosmic inflation provides a sophisticated explanation for the appearance of our universe, even in the absence of concrete evidence. Alternatively, we might be a part of an infinite number of universes, each with its reality and story. What does this signify for us then? Everything we know, including our planet, galaxy, and ourselves, may only be a tiny piece of a massive puzzle if the multiverse is real. This is exciting and humbling, but the hunt for proof is far from over. Will other universes always be hidden in the depths of an infinite multiverse, out of our direct line of sight, or will we ever find proof of them? How can we prove the existence of parallel universes? To unravel some of the universe's most profound mysteries, scientists are investigating some of the oldest hints in the universe, which are relics from the early universe itself. To solve the mystery of the multiverse, these observations are crucial. The cosmic microwave background, or CMB, will be our first topic. Like a time capsule, this dim radiation glow captures the universe just 380,000 years after the Big Bang. We can learn a great deal about the origins of our universe from this light, which is the oldest light visible to us. Scientists search for subtle irregularities and patterns in this ancient light when studying the CMB. These patterns show how galaxies eventually formed and how matter was distributed in the early universe. Here's the interesting part, though. There might have been a noticeable mark in the CMB if our universe had ever interacted with another universe, possibly a nearby bubble in the multiverse. Consider the collision of two soap bubbles. A ripple is produced at the point of contact. In a similar vein, a collision between universes may have created traces in space-time that are still visible to us today. Although there has been no solid proof of such collisions yet, scientists continue to search for them. The CMB has been meticulously mapped by telescopes such as the Planck satellite, which is looking for anomalies that might indicate the existence of a multiverse. The distribution of matter in the universe is a further field of study. Parallel universes likely influence the arrangement of galaxies on the largest scales. Some scientists have hypothesized that interactions with other universes may be the cause of odd alignments or patterns in the universe. The idea of quantum fluctuations comes next. The formation of entire universes, as well as galaxies, may have been sparked by these minute changes in energy that existed during the inflationary era. Additional hints regarding the multiverse may be revealed by observing these fluctuations and comprehending their function. It is challenging to prove the existence of other universes, though. These universes are, by definition, it's like trying to look past a wall in a small area. The search is still ongoing, though. To learn more about the origins of our universe, scientists are pushing the boundaries of theory and technology. Every new finding advances our knowledge of whether the universe is isolated in the vastness of reality, or if we are a part of a multiverse. Is the light from the very beginning of creation concealing the answers? Or will the multiverse always be a fascinating enigma that is just out of reach? Let's now take a brief break from the theories and explore something more creative. How does life in a parallel universe feel? Would it be so different that we wouldn't even recognize it as life? Or would it feel like our reality? Imagine waking up in a parallel universe one morning. Everything appears to be the same at first glance. The air is filled with the familiar buzz of life. The trees sway in the wind, and the sky is a deep blue hue. However, minor details begin to change the moment you step outside. The vehicles may hover rather than move. People may be able to float instead of walk due to the laws of physics. Or history took a different turn. The course of your life, your city, and even your nation changed dramatically. Now picture a different version with minor variations. You might be leading a similar life, but with some changes. You pursued a long-forgotten dream, married someone else, or changed careers. Every choice and chance meeting in a parallel universe could result in a completely different reality. However, what if the distinctions were more significant? The natural laws themselves may be completely foreign in some universes. Stars may never form. There may be no planets. Gravity may be so weak that nothing holds together, or time may be flowing backwards. Could we even consider such a universe to be real? This is a thought-provoking idea. Would we be aware that our senses and brains are set up to perceive the reality we live in, if we were to find ourselves in a parallel universe somehow? It may be impossible to comprehend a universe with drastically different natural laws, much like attempting to visualize a color you have never seen. The most important question, though, is how much those differences would matter in a world with limitless possibilities. Would you be in a different universe? Or would you become someone completely different as a result of the minor adjustments you make to your surroundings, decisions, and situation? Examining what it would be like to live in a parallel universe makes us consider what makes reality and who we are unique. Is it our environment, our life experiences, or something more profound that exists outside of all worlds? One more intriguing question remains, though. Could we ever travel to these universes if they exist? Can we transcend our current reality and enter a different one? Next, we will investigate that. The big question now arises. That's the one that belongs in a science fiction novel. Can we visit other worlds? Can we exit our universe and enter a parallel one? We must first comprehend the limits of our universe to respond to that. Our current understanding of matter, space, and time suggests that the universe is a closed system. We are limited to the physical laws and dimensions that define our reality, much like when we live inside a snow globe. It isn't possible to escape and enter a different universe. However, science loves to challenge the notion of the word impossible. According to some theories, space-time portals that permit travel between universes have flaws in their construction. Consider wormholes, those fictitious passageways that link far-flung regions of space. Wormholes may also serve as bridges between completely different realities, according to some scientists. The catch is this: wormholes would be extremely unstable if they existed at all. Before anyone or anything could get through, They might collapse at the slightest disturbance. But what if we were able to bring about the stabilization of a civilization that was theoretically far more developed than our own, and might possess the technology to use wormholes as entry points to other universes? A strange phenomenon known as quantum entanglement occurs when two particles, irrespective of their distance from one another, display an enigmatic bond. According to some physicists, this enigmatic distant action may indicate more profound inter-universal connections. Is there a way to travel between realities using quantum mechanics? There are, of course, enormous obstacles. We wouldn't know what conditions would be there even if we found a way to travel to another universe. Would it be secure? Could we survive there under the laws of physics? Imagine stepping into a universe where gravity is either so weak that atoms cannot hold together, or so firm that you are instantly crushed. However, there is another query, possibly one that is more philosophical. Should we go to other realities if we could? What would happen if we came across a different version of ourselves? What moral conundrums result from interfering with another universe? Traveling to parallel universes is still a thrilling dream. As of right now, this can be envisioned as a frontier by future researchers and scientists. The act of asking these questions, however, tests our understanding, even if we are unable to look beyond the confines of our reality. It encourages us to think beyond what we currently know. Will we ever construct a bridge to a different universe then? Or will the multiverse, a realm of limitless potential that lies just beyond our grasp, always be unattainable? Let's now address one of the most essential parallel universe queries. What if we engage with a different version of ourselves? It's an intriguing yet unnerving concept, simultaneously posing moral and philosophical conundrums that call into question our perception of ourselves and our role in the world. Imagine running into another of you. Although it might initially feel like looking into a mirror, this reflection isn't real. Their decisions might have been different. Perhaps they're leading the life you've always imagined, or the one you've always feared. What impact would that have on your self-perception? Given how easily their life could have been yours, would you feel pity, envy, or a sense of connection? This is the moral conundrum. Would you be allowed to change their reality? Would you try to learn from them, or even replace them if their life were better? Would you feel compelled to assist them, even if it meant upsetting their world, if it were worse? What about the repercussions of your exchange? Consider the ripple effect. Every decision you make has an impact on those around you in your universe. However, the stakes might be even higher in a parallel universe. A single decision, small action, or conversation could drastically change an entire timeline. And then there's the identity issue. Is there such a thing as the real if you exist in countless versions? You are defined by your decisions, your situation, or something deeper that is true in all realities. This goes beyond simple philosophy. It's a question that goes right to the heart of who we are. What if the other version of you is essentially different? That is the most disturbing question of all. What if they have made decisions that you find incompatible with your moral compass or sense of self? Could you recognize them as you? Or might they feel alienated? Engaging with a different version of ourselves is more than just an intriguing hypothetical scenario. It is a profound reality. It compels us to examine the nature of morality, free will, and the idea of selfhood. It's a thought exercise that asks how much of who we are is unique if we are one of an endless number of possibilities. The most important ethical question is whether we would choose to enter a different version of ourselves if given the opportunity. Or would the dangers to reality itself, to others and ourselves, be too great? Parallel universes are more than just a philosophical or scientific theory. It poses a significant challenge to our understanding of reality and our place within it. From ancient myths about the heavens to the current physics equations, humanity has been trying to comprehend the cosmos for centuries. For a very long time, we have believed that our universe is the only reality, and that everything we know and encounter is contained within it. However, the prospect of parallel universes compels us to face a disturbing reality. What if we only represent a small portion of something much larger? Consider it. Our universe, our home, may not be as special as we once believed if there are innumerable other universes, each with its stars, galaxies, and possibly even life. That insight can be disorienting and even humbling. In an infinite cosmic library, are we only one story among billions? How about you? What distinguishes you as unique if there are countless variations of you, each influenced by marginally different decisions or situations? Are you a singular manifestation of limitless possibilities? Or are you genuinely unique? This concept prompts us to reevaluate humanity's role in the broader context, in addition to challenging our self-perception. As the universe's observers, we have long considered ourselves to be at the center of the narrative. However, if there is a multiverse, we are not at all at its center. We are one thread among countless others in a vast, complex tapestry. Here's the paradox, though. The idea of parallel universes can make us feel small, but it can also make us feel incredibly connected. Every option, every possibility, and every moment has value if reality is limitless. It serves as a reminder that despite the vastness of the universe, our deeds still hold significance because they are part of something far greater than ourselves. The concept of parallel universes is not just about what exists outside of it, but also about how we perceive our place in the universe. Are we adventurers looking for solutions to the greatest mysteries? Or are we merely characters in a story that is so big and intricate that we might never understand it completely? In any case, the journey compels us to view the world and ourselves from a completely different perspective. Our understanding of the universe is broadened by the idea of parallel universes, which also directly contradicts some of our most ingrained assumptions about fate, free will, and the nature of consciousness. First, let's talk about free will. We like to believe that our decisions define who we are. Every choice we make, no matter how big or small, feels like a special thread in the tapestry of our lives. However, what if every decision you could make occurs in the multiverse? You may have taken one path in one universe and a different one in another. Do you have free will if every possibility is realized somewhere? Or are you merely acting out one of countless possible outcomes? And then there's destiny. Does the existence of parallel universes imply that everything is predetermined? Does it matter what decisions you make if every possible outcome exists in some reality? Does the fact that there are an infinite number of possible outcomes mean that there isn't a set result? This paradox prompts us to reevaluate our definitions of control and the validity of the concept of control in a multiverse. What about awareness? With so many different versions of yourself, who are you? Is this universe the only one with your consciousness? Or is it related to all of your counterparts in other realities in some way? The question of whether consciousness is a purely physical phenomenon or something more profound has long been debated by philosophers and scientists. This argument is elevated to a new level by the concept of the multiverse. Is it possible that our thoughts and sense of self are merely a single piece of a more complex, interconnected whole? This is a thought exercise. Would you feel the same if you could see all of your incarnations in all of the universes? Or would the distinctions, whether minor or significant, cause you to reevaluate your identity? The idea of parallel universes transcends scientific boundaries. It compels us to address some of the most important issues regarding life in general. It calls into question the very concepts of identity, choice, and individuality, leaving us to ponder what it truly means to be in a world of limitless possibilities. These are difficult questions to answer, but they serve as a reminder that multiverse exploration is more than just traveling through time and space. It's an exploration of the limits of our knowledge. Our understanding of the universe and ourselves may be irrevocably changed by this adventure. In addition to challenging our perception of reality, parallel universes open up new avenues for investigation. The way we view the universe and our place in it could be altered entirely if even a small portion of the multiverse theories turn out to be accurate. Just think of what could be. We may discover the reasons behind the unique characteristics of our universe if we find evidence of other universes. Because of this, the laws of physics have been adjusted to permit stars to form planets, which in turn allows the evolution of life. We might discover universes with drastically different conditions while researching other realities, which would help us better understand the delicate balance that makes our universe unique. What about reality's very beginnings? Parallel universes may hold the key to understanding the universe's origins. According to some scientists, research into the multiverse may help determine whether the Big Bang was a unique occurrence or merely one of an infinite number of beginnings in an endless cycle of cosmic creation. Additionally, there is the potential for technological advancements. Imagine if we could use the concepts of parallel universes, such as the enigmatic connections that quantum mechanics suggests. Could those principles be used to solve previously unsolvable problems, like traveling faster than light, limitless energy sources, or even novel approaches to space exploration? The most important findings, however, come from what universes have in common, rather than from their differences. We may find universal truths, patterns, or principles that apply to all realities by researching the multiverse. The most important questions concerning life may become clearer to us as a result of these revelations. We ponder the ultimate fate of reality, the nature of consciousness, and the existence of something beyond nothing. The potential is astounding, even though these discoveries are still far off and on the very edge of our imagination. If true, the multiverse expands not only the universe, but also the limits of human understanding, encouraging us to investigate not only the universe in which we currently reside, but also the countless opportunities that exist beyond it. Ultimately, curiosity is more important than science in the pursuit of knowledge about parallel universes. It's about the human desire to find the answers to the most significant questions, to go beyond our current understanding, and to welcome the unknown with unbridled curiosity and open minds. Our findings have the potential to alter not only our understanding of the universe, but also our understanding of ourselves. The idea of parallel universes is not merely a philosophical or scientific theory. It's a call to challenge our conception of reality and broaden our imagination. Few ideas are as compelling or thought-provoking, engrossing us in inquiries that appear to transcend our comprehension. These universes offer a glimpse into countless possibilities, if they exist. Worlds where the laws of physics may not be the same as our own, where history was different, or where we are leading lives we can only imagine. The pursuit of parallel universes compels us to broaden our horizons and raise issues that transcend the realms of philosophy and science, even though they may never be fully realized. At their core, parallel universes serve as a reminder of the vastness of reality. It's exciting to know we're part of something so vast, enigmatic, and exquisite. Still, it's also humbling to consider that our universe may be only a tiny portion of an infinite multiverse. The most important thing we learn from this exploration about ourselves, our place in the universe, the decisions we make, and the insatiable curiosity that keeps us asking, looking, and wondering, is more important than any evidence of other realities. Consider that in a universe full of mystery, Every possibility might exist somewhere as we come to the end of this journey. In terms of your decisions today, what does that mean? How does it affect your perception of the infinite unknown, your world, and yourself? The questions will always drive us forward, even if the answers are out of our grasp. Therefore, keep this in mind as you return to your universe. We come closer to comprehending the remarkable reality we live in, with each question we ask and each scenario we envision. Who knows? A different version of yourself is asking the same questions, dreaming, exploring, and looking for answers in a different reality. Set aside your preconceived notions about the universe. What if a telescope discovered a galaxy that shouldn't be there, or a signal that might indicate life? We are no longer dreaming. The James Webb Space Telescope is revolutionizing our knowledge of the universe. It's more than just stargazing. It's looking back in time and bringing up information that causes scientists to doubt everything. They had no time to form galaxies, planets with substances that beg for life. A chaotic universe is too ideal for structures. Science fiction is not what this is. It is an actual, quantifiable phenomenon that is fundamentally altering our understanding. The universe doesn't follow our rules. The pieces of the cosmic puzzle it is presenting to us don't fit together. We can't ignore what Webb's infrared eyes are seeing. From galaxies born when the universe was a baby, to signals 124 light-years away. We're discovering questions we didn't know to ask in addition to answers. We're exploring 4 groundbreaking findings today that radically alter our knowledge. We have found a planet that may contain a gas that could be a sign of life. It's a spiral galaxy that resembles home too closely. Galaxies are so old they defy time, and auroras on Neptune don't add up. This is the universe speaking, and it's shouting, not whispering. Stay tuned to find out what Webb discovered and why it made a huge difference. What if there is life on a planet 124 light-years away? A discovery that is difficult to explain was made on K218b by the James Webb Telescope. K218 is not merely another celestial body. The exoplanet K218b circles a faint red dwarf in an area where liquid water can exist. It was simply fascinating for years, too large to resemble Earth and too far away to garner media attention. Then everything changed when Webb turned its mirror. It searched for chemical hints in the planet's atmosphere by filtering light through a spectrometer. Scientists were stunned by what they discovered: dimethyl sulfide. Life is the source of this gas on Earth. When they die, tiny marine life, like plankton, pumps it out. It's the sharp, transient scent of salty sea air. It requires constant replenishment because sunlight quickly depletes it. This signal, which Webb picked up in the skies of K218b, indicated that life was present. This signal was a loud shout, rather than merely a whisper. Compared to Earth, the levels were incredibly high. Consider it similar to identifying smoke from a fire throughout the galaxy. Something is alive, but you're not sure what's burning. The thick, hydrogen-rich atmosphere of this planet most likely conceals a deep ocean. It isn't fish or forests if there is life. Maybe microorganisms are churning out chemicals or something else we can't even fathom while floating in that alien sea. There are enough specks to be suggested by the signal. It might be an ecosystem, a living world that is massively pumping gas. But wait, science does not assume that aliens exist, but there's a catch. Other chemicals, including methane, can mimic this infrared signal. They double-checked because mistakes happen. The signal remained strong. It became more apparent. According to estimates, the signal's strength was 1,000 times greater than Earth's. That isn't a bug. Is that real? Is it a gas pocket? A strange volcano or geology? Perhaps. However, Dimethyl sulfide is not produced in this way by any non-living processes on Earth. No, we've looked. We need new regulations if K2 and 18 are acting in such a lifeless manner. The cosmic puzzle gets complicated at this point. K218 is not a far-flung theory. Even though it's 124 light-years away, it can still haunt us, despite being close enough to study. We're not discussing dreams or fossils if this is life. Right now, we are discussing a living thing that is making its mark on the sky. Although Webb's other teams and telescopes will rule out chemistry and physics, as well as any tricks or false alarms, life becomes the only reasonable explanation when all others have failed. That makes all the difference. We're not merely inquiring about our loneliness. What else is being measured is out there. What is the chemistry of it? How does it manage to live? Is it a stranger or something like us? The signal from K218 is a crucial element that demands attention. Previously, we believed that alien life was a problem for the future, a thing for science fiction or starships, but now it could be right in front of us. A signal from a nearly touchable planet. The story doesn't end here. This is the beginning. The signal from K218 suggests life. However, what if the universe created galaxies that were too ideal for its laws? What if a galaxy appeared billions of years too early, but still had the appearance of a home? Webb discovered one, and it's completely upending our timeline. The James Webb Telescope has detected a spiral galaxy called Xulong, also known as Torch Dragon. It's not just a long way off. It shines from a very long time ago when the universe was only 1 billion years old. Everything should have been in disarray shortly after the Big Bang. Imagine the early universe as a stormy sea where stars and gas collide, combine, and split. Back then, galaxies should have been chaotic blobs rather than neat spirals like the Milky Way. Spirals require time. It is time for a disk to spin steadily, for stars to line up into clean arms, and for gravity to calm down. We assumed that would take billions of years. Xulong disobeys the regulations. Those arms balance that structure. Instead of being freshly formed in a cosmic explosion, it has been at rest for a very long time. In a quarry where rocks are still being blasted, picture finding a polished statue. What shouldn't have been there was captured by Webb's infrared eyes. The universe is already an adult, but the light we see left Xulong when it was a baby. It has tight spiral arms. It is stable and has a bright core. This indicates that it formed a few 100 million years after the Big Bang, which is even earlier. The science is here. Redshift is the method used to measure this distance. Stars turn redder as a result of the way light stretches as the universe expands. Xulong is located 12.5 billion light-years away, based on its redshift. It's more than just a figure. There is an issue. According to our models, spirals form later, after galaxies have cooled and experienced messy collisions. Xulong disagrees, and it's not alone. Webb's galaxy-like discoveries were too neat for their time. This is another piece of the cosmic puzzle, and it is not part of the puzzle. Why is this important? The universe was forming much earlier than previously thought if spirals were forming at such a high rate. Back then, gravity was more powerful. Perhaps stars were drawn together like a strong magnet by dark matter, an unseen force that acts as a kind of glue. Otherwise, our entire timeline is off. Some scientists are reconsidering how early gas clumped. The wilder theory is that the first stars burned out more quickly, spitting out material for galaxies like Xulong. The rules of the universe were slightly different in those days, but enough to move things along quickly. There is more than one galaxy at issue here. The focus is on what is feasible. Xulong-like spirals are stable. It is in these kinds of conditions that stars endure. Planets form, and life may thrive. These early life-friendly locations might have appeared much sooner than we anticipated if they had existed. That is significant. This suggests that our Milky Way exists. Our house isn't particularly unique. It's just one of many people who might arrive late for the celebration. The universe didn't waste time, Geelong tells us. We believed it was still setting up shop, but it was building homes. Webb is not finished. It continues to identify these early spirals, each of which challenges our preconceived notions. Geelong is not an exception. It's a hint. There are more pieces in the cosmic puzzle than we first thought. What's so disturbing about this discovery is that we're not just looking at a galaxy, we're looking at a universe that has existed before us. The past appears too similar to the present. Geelong's early spiral defies the stars, but what's lurking closer in our cosmic backyard? It's not what we anticipated when the James Webb Telescope turned its attention to Neptune. The most isolated planet in our solar system, Neptune, is a remote, frigid, and largely unexplored world. The majority of our knowledge is based on a single short visit made by Voyager 2 in 1989. Since then, ground-based telescopes have only provided astronomers with hazy views of Neptune. No one had the idea to aim our deep space champion Webb at a nearby planet, but they did. And it saw more than just pretty lights. It was an unfitting piece of a puzzle. Unlike Earth's soft, shimmering northern lights, Webb saw the auroras on Neptune glow at its poles. These are untamed and disorderly, propelled by unknown forces. Imagine figuring out a strange signal on a radio that you thought was broken. There's a loud broadcast going on. Neptune's haze was pierced by Webb's infrared vision, which enabled him to map heat and chemistry in previously unexplored ways. It saw hotspots where there shouldn't be heat, cold patches that resist the sun's feeble hold, and auroras pulsing in strange patterns. Auroras occur on Earth when particles charged by the solar wind collide with our magnetic field. Although it's a mess, Neptune also has a field. Unlike ours, its magnetic field is lopsided and tilted. From the sun, those particles crawl through space, taking an eternity to reach it. Webb, however, noticed something else. Fluctuations in temperature that don't add up. A few places cooled too quickly. Some burned hotter than they ought to have. We don't know the recipe, but Neptune is creating its weather. The data is here. Chemical shifts in Neptune's atmosphere were detected by Webb's instruments, which were tuned for distant galaxies. Although methane absorbs light in peculiar ways, its behavior is influenced by something. Maybe reactions we haven't yet recognized or magnetic storms. There's more to the auroras than just a show. They are hints of a planet we thought we knew. The magnetic field of Neptune is a complex phenomenon that defies our current models. Energy leaking from the planet's interior could be the cause of those hotspots. Those cold zones may indicate unexpected gas sinking. We don't know. The point is that Webb took more than one picture. It raised issues we hadn't considered. This is not a tale about a distant celebrity. It's in our system right here. While we chased galaxies, Neptune was out there, remaining silent. Webb is now letting us know what we were missing. Voyager's flyby was mentioned in the sample, but Webb's gaze is more intense and focused. Auroras aren't the only ones. It's a planet that defies our laws of chemistry, heat, and storms. And you're not alone. Neptune's twin Uranus may be up to similar pranks. We haven't done enough searching. Webb is demonstrating that our outer planets are strangers. Why is this important? The cosmic puzzle has another crack in it. We believed that we understood the Earth, Mars, and Jupiter in our solar system. Hold on though, Neptune is saying. There's more. Neptune's auroras provide clues about magnetic, chemical, and perhaps even geological forces that may help us understand how planets work. It has an impact both locally and internationally. What other aspects of Neptune might we be missing if our understanding is wrong? Oceans surround the moons. It's not just a pretty view, even if we can't predict it. It serves as a warning. Even in our backyard, the universe never ceases to amaze us. Webb is still working on Neptune. There will be more observations soon. They might solve new mysteries or decipher the code on those auroras. In any event, this telescope is upending our assumptions. It urges us to examine even the locations we thought we knew well in greater detail. The auroras on Neptune are more than just lights. They serve as a signal. We're only now beginning to pay attention to what's happening out there. Secrets shine in the auroras of Neptune. However, what if galaxies formed without authorization? They're breaking all the rules, according to the James Webb Telescope. Introducing JD's GS-Z14. It's a time bomb, not just a galaxy. When the universe was just 280 million years old, Webb noticed it shining. The universe was in a state of chaos at the time, with matter still forming and gas swirling around hardly ignited stars. There shouldn't be any galaxies yet. They require time. It is time for stars to cluster, for gas to cool, and for gravity to form a solid object. Imagine attempting to bake a cake while it's still warm from the microwave. JD's GS-Z14 isn't raw batter, but you shouldn't get a cake. It's a massive, compact, and bright cluster with millions of stars, comparable in size to a galaxy. This is nuts. According to our model, galaxies form over billions of years. First, you need stars. Small, fast-burning, young stars composed of hydrogen and helium. They eject heavier substances, such as carbon, during an explosion. It cools, collapses, forms new stars, and gradually gives rise to galaxies. That makes JADISGSZ14 laugh. It has mass, shine, and structure, all of which were present before the universe had an opportunity to expand. Imagine locating a skyscraper constructed before the development of steel. The receipts are with Webb. Redshift is used to measure this. The age of 13,500,000,000 years is indicated by the redshift of JADE's GSA-14-0. It's not just a long way. It isn't feasible, or it was. The mass of this galaxy, compressed into a 500 light-year radius, is equal to 100 million suns. Although this galaxy is small, it possesses considerable power and is intricately connected to the rest of the universe. Webb's results are comparable to those of galaxies that emerge far too early, too bright, and too large. This is where the cosmic puzzle starts to come apart. Something accelerated the process. Perhaps matter was pulled together like a cosmic tow truck by dark matter, that unseen scaffolding. The first stars were massive giants that quickly exploded, giving rise to the galaxies. Or the early laws of the universe were less strict. The force of gravity is greater. Time is stranger. Researchers are rushing. According to some, gas clouds collapsed more quickly than anticipated. Some believe that dark matter is more significant. The more daring theorists are conjecturing about physics concepts that we haven't yet thought of. Why does this matter? Not only are these early galaxies old, they are revolutionary. The universe would be prepared for business much sooner than we had anticipated if they formed this quickly. Stars in stable galaxies are stable. Planets are stable stars. Planets represent opportunities for life in the early universe. A pretty dot isn't all that JADESGSZ14 is. The universe didn't wait around, as evidenced by this. While we were busy creating rules that it doesn't follow, it was rapidly growing. By accumulating these discoveries, Webb is uncovering additional early galaxies that challenge our knowledge of the chronology. They aren't anomalies, they follow a pattern. This piece is heavy, and the cosmic puzzle continues to expand. This indicates that the universe was never sluggish. What's eerie is that it was constantly in a hurry, spinning out galaxies as though it had somewhere to be. We believed we understood the universe's story, but Galaxies Z14 tells us we're misreading it. Webb is demonstrating to us not only the stars, but also the amount of knowledge we still need to acquire. The discovery of early galaxies has significantly altered our understanding of the universe, but what do these findings mean for us today? The James Webb Telescope is rewriting our perception of our position in the universe. Check out what we discovered. The gas that K218b is pumping out could mean the difference between life and death. J Long's spiral appeared much too soon and seemed to be home before it should have. In our backyard, Neptune's auroras are dancing with secrets. The early formation of the galaxy, JADE SGSZ 14, indicates that the universe expanded quickly. These are not merely celestial specks. They give us a profound message by being essential pieces of a cosmic puzzle. The universe is not what we once believed it to be. It's not quiet, it's not empty, and it's not slow. Before we had a clue, it was busy creating galaxies, possibly a lifetime endeavor. This alters the game. We used to inquire about our loneliness. We now want to know how many other people are out there. Are we unique, or merely a single piece in a vast puzzle? There are no apparent answers in Webb's data. Galaxies are too old, it suggests. It's too strong a signal. The light is too strange. Every one of them challenges our preconceived notions. And it's not finished yet. There will be more discoveries soon. More inquiries. More parts. Now what? Continue to look up? We are finally listening to what the universe has to say, not through dreams, but through intricate data. The universe that Webb is presenting to us is vibrant, restless, and full of surprises. Are we prepared to see what comes next? Is there still a puzzle to solve? It's only the beginning. A mysterious force is at work in far-off galaxies. Our sky is illuminated by an odd flash 3 times a day. It has hundreds of times the power of all the nuclear weapons in the world. However, it wasn't created by humans. Additionally, it has the potential to eradicate all life on Earth if it happens to be near enough. The majority of people on Earth are ignorant of the possible risks in space. Consider this. A deadly burst of energy hurtles towards our planet from the explosion of a massive star in the Milky Way, our galaxy. The most massive explosion since the Big Bang is a gamma-ray burst. There are no indications that a disastrous event is imminent. Then it hits. The high atmosphere is heated by the radiation that is pumped up. Our ozone layer warms up. Humans are burned to death throughout the atmosphere by radiation 100 times the lethal dose. Global temperatures increase as the ozone layer thins. This brings on hurricanes, tsunamis, and storms. The majority of life on land and water surfaces burns up. This might sound like science fiction, but it could happen if Earth was struck by a gamma-ray burst that was 100 light-years away. The brightest explosions in the universe are gamma-ray bursts. Given their distance, they must possess a great deal of power, but their brightness hasn't diminished. As much energy as the Sun will emit over its 10 billion years. Given that the universe is known to contain a large number of planets and stars, a gamma-ray explosion could have destroyed a wide variety of cultures. This unusual radiation burst was first discovered in the 1960s. Initially, due to the brightness of these gamma-ray bursts. The majority of scientists believe they originated in the Milky Way, our galaxy. This is due to several factors. One of them is that the energy is nearly too great to be true if they are not in the galaxy. However, the burst lasted only a few seconds before vanishing, so even the most powerful telescopes at the time were unable to pinpoint their location or distance. Then, however, scientists began to question their afterglow. For days or even weeks, the majority of space explosions leave a glowing trail in their wake. The afterglow of a gamma-ray burst was finally captured by satellites with improved optics and X-ray detectors in the late 1990s. It was discovered that the source of gamma-ray bursts is located millions and billions of light-years away outside our galaxy. They, therefore, needed to have extraordinary power. 1,000,000 trillion suns would be the same brightness as the gamma-ray burst. This enormous explosion could wipe out all life on Earth. However, why do they occur? The death of a star at least 10 times the mass of the Sun is what causes explicitly a typical gamma-ray burst. These kinds of massive stars are uncommon, though. A black hole is created when a massive star collapses. Black holes are created when a mass of matter contracts to a density that prevents light from escaping. According to experts, some stars are resistant to the gravitational pull of the black hole. Consequently, a rapidly spinning disk of matter develops around it. Plasma jets emerge from the poles, where it spins in a matter of seconds. Dangerous gamma rays are released into space by these energy beams. The gamma-ray bursts are expelled simultaneously. To a great extent, the collapsing star explodes or goes supernova. Because they consume a significant amount of energy and concentrate on a small region of the sky, gamma-ray bursts are potent. We see only one of the 300 gamma-ray bursts, because only one of them is aimed at us. The destruction of the Earth could resemble the end of the world, even if a gamma-ray burst happened 1,000 light-years away instead of 100. A gamma-ray burst would be about 500 times brighter than the Sun, and release gamma rays if it happened within 100 light-years of Earth. The energy released into Earth's upper atmosphere would be equivalent to the detonation of 100,000 megatons of nuclear bombs. There would be a decrease in ozone. In addition to acid rain, there would be flash burns, vegetation incineration, and possibly even nuclear weather. Globally, many species are at risk of extinction. Because gamma rays cannot pass through the Earth, you cannot get flash burned on the opposite side of the planet, which makes it unique. However, the consequences of altering the atmosphere's composition and ozone depletion would eventually catch up with us. Nobody can predict what will happen in that scenario. The likelihood of this terrible situation happening in Earth's history is 1 in a trillion. If you get caught in the beam, it will be a bad day. You should avoid this kind of energy because it is strong and can break down your molecules. Humanity is currently defenseless against gamma-ray bursts that happen close to Earth. They travel at the speed of light, which is 186,000 miles per second. They would have already hit our planet by the time we were able to detect them. The Earth and any living things that come into contact with their birth site could be at risk from gamma-ray bursts. Gamma-ray bursts may have caused some of the mass extinctions on Earth. The worst was most likely the one that wiped out Ordovician and Silurian species 450 million years ago. Animals that lived close to the ocean's surface were struck far more severely than those that lived far below. This is in line with the expected outcome of a powerful gamma-ray explosion. Astronomers estimate that gamma-ray bursts occur roughly once every few 100,000 years in a galaxy the size of the Milky Way. You have to come very close to being harmed by one, even though they can be awful. About once every 5 million years, there is a gamma-ray burst, which is close enough to have an impact on life on Earth. In other words, there have been approximately 1,000 events since the Earth's formation, which occurred some 4.6 billion years ago. Although there is a chance of a near gamma-ray burst, it is not so great that you should be concerned about it, unless you're hoping to live for 5 million years or more. Although humanity was unharmed by the gamma-ray explosion, this incident illustrates the wide-ranging consequences of such an event. Don't worry. Gamma-ray bursts pose very little threat to Earth. Astronomers have examined all of the closest candidates for gamma-ray bursts, and none of them are close enough or orientated to strike Earth. So what are your thoughts? Earth shines like a sapphire gem in our solar system. We live our lives without realizing that trouble might be lurking in deep space. The paths that Earth and most other objects take around the Sun are predictable. Things are calm and easy most of the time, but occasionally they become violent and crazy. Earth can be struck by space rocks, electrocuted by hazardous space weather, and jostled, and threatened by the cosmic forces and energy of the object. The Earth is traveling through space at significant risk, and frequently runs into hazardous situations. Since there is nothing you can do, you hope nothing crosses as you are traveling quickly along a predetermined path. He oversaw the lunar module during the 1969 Apollo 9 flight. An asteroid called Apophis is getting too close to be deemed safe, so it is being warned about the dangers it poses. Since the likelihood of impact was relatively high, everyone immediately noticed him. It was much higher than any effect probability we had previously observed. Schweikart provides a terrifying real-world example to highlight the catastrophic effects of even a small asteroid, like Apophis, colliding with Earth. Around 7:15 a.m. on June 30th, 1908, a stream of flaming gas trailed behind a half-football field-sized object that was hurtling down from space at roughly 34,000 miles per hour. The fireball struck Earth's atmosphere within minutes and exploded violently close to Siberia's Tunguska forest. Because of this, the explosion was the biggest in the planet's history. 8 million trees in an area larger than half of Rhode Island were burned when the explosion split the waves. No one was killed directly by the explosion because it occurred in an area with few people. That asteroid would have affected Europe rather than Siberia if it had struck a few hours later. Additionally, 1 million people would have perished if it had detonated in mid-air over one of the largest cities in Europe. The Tunguska explosion has been the subject of controversy for the past century. Many scientists now believe that the explosive trigger was an asteroid. Amazingly, it didn't even hit the ground. Instead, it exploded 5 miles above the frozen ground of Siberia. It is like an egg hitting concrete when it hits the lower atmosphere at a speed of roughly 50,000 miles per hour. The Siberian explosion was approximately 1,000 times more potent than the Hiroshima blast, releasing energy equivalent to 15 megatons of TNT. This would have disastrous effects on a large city. Scientists referred to these intruders as near-Earth objects, or NEOS. They are the remains of asteroids and comets that were left over after the planets formed. Comets pass through the Oort cloud, which is a region of the Kuiper belt that stretches beyond Neptune. Asteroids follow a curved trajectory between Jupiter and Mars. However, their orbital journey isn't always the same. Because asteroids orbit in a reasonably ordered belt between Mars and Jupiter, we don't have to worry about them too much. Astronomers become concerned, though, when one escapes, and all that mass and energy is focused on Earth. Cosmic debris is frequently jolted out of orbit and headed towards Earth. The thick atmosphere of our planet evaporates most of it. However, a bigger object has the potential to penetrate Earth's atmosphere and hit the surface. If you want to search the universe for the forces that would kill us, asteroids are a real and serious threat. It will happen again, just as it did before. An asteroid the size of a small city fell out of the sky 65 million years ago. With the force of 100 million megatons of TNT, it exploded in Mexico's Yucatan Peninsula, close to the town of Chicxulub. In this image, we witness Earth blasting billions of tons of its crust into space, forming a blanket that blots out sunlight, uprooting the food chain, and eradicating innumerable species. It is thought that one of the reasons the dinosaurs went extinct was due to the severe impact. Although they are often viewed negatively, asteroids play a crucial role in our existence. Trying to avoid becoming T-Rex hors d'oeuvres, our mammal ancestors were on the move. The demise of T-Rex. Primates emerged as a result of our mammal ancestors' ability to evolve into something more ambitious than a root due to the ecological niche that was created. We also have humans among the primates. Oddly enough, though, the same type of cosmic boulder that allowed humans to survive might eventually exterminate us. The results of NASA's 1998 search for all near-Earth objects at least half a mile across, as requested by Congress, were disturbing. Near our location, there are over 850 near-Earth objects. Our closest and most perilous space companions are these asteroids. Finding these near-Earth objects is like keeping an eye on storms. You learn more about its trajectory as you observe it every day, and you can calculate its size, direction, and the speed at which it would strike Earth in the event of a collision. NASA's Space Guard survey has detected more than 90% of all NEOs considered dangerous using telescopic technologies. These terrifying objects have the potential to strike Earth with greater force than all of the current nuclear weapons. Mass extinction could result from such an impact. Although we wouldn't anticipate one occurring every few 100,000 or millions of years, it could eradicate various segments of the populace if it did. Although they occur infrequently, some events have a profound impact when they do. They would have a devastating impact on the entire world if they struck Earth. In addition to using strong shockwaves to destroy an entire continent, they would also launch debris into the air, which would land everywhere and heat the atmosphere to 1,000 degrees. And every piece of vegetation on the planet where that occurs would catch fire. Congress has requested that NASA locate all NEOs with a diameter of 500 feet, which is equivalent to the size of the Colosseum in Rome, because smaller objects could also result in catastrophic consequences. Such a large object could destroy a city or even a small state. Rather than the asteroids they have already identified, scientists are more concerned about the ones they have yet to find. There are currently approximately 2,000 objects for which we cannot be certain will not strike Earth. With today's technology, we can prevent near-Earth objects from ever striking Earth. Now, we can alter the local solar system to improve our quality of life. Whether or not we will become like the dinosaurs is the question. Given the significant changes that have occurred since the Earth's formation, it isn't easy to accept that it has existed for more than 4.5 billion years. Every year, asteroids enter our orbit and continue to strike our planet like a boxer. But one day, Earth might be destroyed. We've discovered that near-Earth objects constantly pass us by, and we're getting better at modifying our environment to keep ourselves alive. Apophis is a rock in space. This roughly 750-foot diameter pockmarked rock approached Earth in February 2004. It is now expected to come dangerously close to Earth once more on Friday, April 29th. Therefore, Apophis will be closer to us in 2029 than our Earth-circling Rome communication satellites. Apophis will fly past Earth if you're in the right place. That rock will get as close as that. Binoculars won't even be necessary. In 2029, Apophis will miss Earth more than 99% of the time. It might, however, go through a gravitational keyhole, which is a tiny, half-mile-wide region in space, if it passes the Earth precisely at 1,893 miles. If this happens, Apophis may be deflected by the Earth's gravity, changing its course. On April 13, 2036, 7 years after this deflection, Apophis might return and strike Earth. Apophis's orbit would be bent by the Earth's gravitational pull, growing to a size that would allow it to return and strike the planet 7 years later. As of right now, the odds of Apophis striking in 2036 are 1 in 45,000. Instead of just knowing that there is a 1 in 45,000 chance that it will strike Earth, you want to know if the odds are 1 in 100, 1 in 10, or 1 in 1. Apophis needs to be treated the same way as any other natural disaster. You can make a map because you know the orbit's angle and the date of the impact. It begins in western Siberia, travels through Central America, crosses the Pacific Ocean near California, and ends in Western Africa. Scientists have developed a concerning theory about potential Apophis strikes. The asteroid could strike the Pacific Ocean off the coast of California with the force of over 1 million megatons of TNT. A hole 5 miles wide and 9,000 feet deep would be created in the water by such an impact. Unimaginable human casualties would result from tsunamis that hit the coast with waves as high as 50 feet. It's not suitable for that kind of thing if a rock 1,000 feet across hits the ocean. Researchers are now trying to determine how to prevent such a cosmic strike from occurring. Some people worry that detonating an asteroid might make matters worse by sending more fragments, rather than just one, our way. Experts' new objective is to change the trajectory of asteroids that might strike Earth. To avoid striking the Earth, alter its velocity by 10,000 miles per hour. We can change an asteroid's course if we have enough time to notice it. Launching a human-crewed mission is the most challenging concept, despite a space probe having previously landed on an asteroid. Astronauts could install a radio transponder on the rock after landing to monitor its location. The UN is currently working on a treaty that will specify who will be responsible for avoiding deadly asteroids. It would be a true crime if we continue to act carelessly and do nothing, knowing that this will occur. An international disaster response would be necessary if an asteroid were to strike Earth. To effectively handle the asteroid threat, the public, emergency, and disaster management organizations must also receive training. Everyone needs to understand the seriousness of the threat and how easily it can be mitigated. Aside from all of this, scientists and amateur astronomers can collaborate to protect our planet. There are many minor and potentially hazardous asteroids in the universe that amateur astronomers can help find. Are you interested in becoming an amateur astronomer? You might be one of our house's guards. Some stars could engulf our entire solar system and still have space left over because they are so big and bright. You will pass them tonight, not as a spectator, but as a traveler. They are the cosmic titans, the behemoths that burn fiercely, live quickly, and explode with enough energy to form galaxies. The reason you are here is because of their deaths. Additionally, some of these stars are enormous. One would swallow up Earth, Venus, Mercury, and even Mars if it were visible. You've come to meet these titans. These giants, though magnificent, are ephemeral. They return their matter to the universe that created them, live quickly, and die spectacularly. As you get closer, you realize that they are both fundamental and fascinating. You wouldn't be here without them. The elements in your blood, bones, and air were forged by their collapse,